Think about the names you learned in school when it came to ancient astronomy: Ptolemy, Copernicus, maybe even Aristarchus or Hipparchus. These are the celebrated giants, the ones whose ideas echoed through the centuries and shaped our understanding of the heavens. But what if I told you they were only the tip of the iceberg? That for every famous name we remember, there were dozens of others, brilliant, curious, determined individuals whose work laid the foundations, asked the daring questions, and mapped the stars long before those household names ever looked up at the night sky. These are the forgotten astronomers of the ancient world, the missing pieces in a story we thought we knew. Picture this: a lone observer on a clear night thousands of years ago, tracing patterns among the stars without telescopes, without calculators, armed with nothing but patience, intuition, and an unshakable desire to make sense of the cosmos. These men and women from cultures spread across the globe didn't just watch the sky, they measured it, predicted its movements, and created systems that would influence science for generations. Yet today, their names have faded into obscurity, their contributions overshadowed by time, political change, or simply the uneven hand of history. But their legacy is still there, written in the stars and waiting to be rediscovered. That's exactly what we're going to do in this video. We're setting off on a journey to meet 30 of these extraordinary minds, thinkers from Babylon, Egypt, India, China, Greece, and beyond, who dared to decipher the universe with nothing but their intellect and imagination. You'll hear stories of innovation that rival modern science, of star charts etched in clay, celestial models carved in stone, and predictions so accurate they still inspire awe today. This isn't just a list of names, it's a recovery mission, piecing together a richer, more complete history of human curiosity and our timeless quest to understand the cosmos. So settle in, because we're about to shine a light on the forgotten astronomers who helped us see the universe. Our journey begins not with a king or a philosopher, but with a figure shrouded in both legend and scientific prowess, a woman known as the Witch of Thessaly. In the 2nd century before the Common Era, in a region of ancient Greece, Aglaonice practiced an art that to her contemporaries seemed nothing short of pure magic. She possessed the terrifying and awe-inspiring ability to make the moon disappear from the sky. Of course, we now know her power was not supernatural. It was the product of a brilliant and meticulous understanding of astronomy. Aglaonice had mastered the complex cycles of lunar eclipses. By studying the patterns passed down through generations, likely from even earlier Babylonian astronomers, she could predict the exact moment the Earth's shadow would begin to creep across the face of the full moon. Imagine the scene. She would announce an eclipse in advance, gathering people to witness her supposed command over the heavens. As the moon gradually darkened and was swallowed by shadow, her reputation as a powerful sorceress was cemented. The ancient writer Plutarch even mentioned her, noting that she was part of a group of women astrologers who, as he put it, boasted of being able to draw down the moon. This phrase, drawing down the moon, is incredibly evocative. It perfectly captures the thin line she walked between being a respected scholar and being feared as a mystic. In a time when women were largely excluded from formal scientific pursuit, this mystical reputation might have been the very thing that allowed her knowledge to be acknowledged and remembered, even if it was mischaracterized. Aglaonice's story is so much more than a curious historical footnote. She represents one of the earliest documented female astronomers in the Western world, a testament to the fact that the drive to understand the cosmos has never been limited by gender. Her legacy is a powerful reminder of how easily science can be misinterpreted as magic by those who do not understand its principles. She used pattern recognition, data collection, and prediction, the very bedrock of the scientific method, long before it was formally defined. While the men of her time might have received credit for their philosophical theories, Aglaonice was a practical scientist, applying celestial mechanics to create real-world, observable results that, for her audience, were indistinguishable from witchcraft. From the shadowy realm of Aglaonice's lunar predictions, we now travel into the brilliant, sun-drenched clarity of a mind so far ahead of its time that the world simply wasn't ready for it. In the early 3rd century before the Common Era, on the island of Samos, a mathematician and astronomer named Aristarchus looked at the cosmos and saw a truth that would not be widely accepted for another 1800 years. He proposed a breathtakingly simple yet utterly radical idea that the sun, not the Earth, was the fixed center of the universe and that our planet was just one of many revolving around it. This was not a wild guess. Aristarchus was a rigorous geometer, and he set out to prove his theory with painstaking calculations. In his only surviving work on the sizes and distances of the sun and moon, he attempts to measure the cosmos using nothing but careful observation and geometry. His method was ingenious. He realized that during a half moon, the sun, moon, and Earth form a right triangle. By measuring the angle between the sun and moon from Earth at that exact moment, he could, in theory, calculate the relative distances to each. His measurement of that angle was 87 degrees, which led him to conclude the sun was about 20 times farther from Earth than the moon. While we now know the actual angle is closer to 89.8 degrees and the sun is nearly 400 times farther away, his geometric principle was flawless. It was the first scientific attempt to scale the heavens, and it established a method that would be refined for centuries. He also used lunar eclipses to estimate the sizes of these celestial bodies. By observing how long it took for the Earth's shadow to pass over the moon, he deduced that the Earth's shadow was about twice the width of the moon itself. From this, he calculated that the sun was vastly larger than the Earth, another compelling reason, in his mind, for the larger body to be at the center of the system. So why did this brilliant heliocentric model fade into obscurity, only to be rediscovered and championed by Copernicus in the 16th century? The reasons are a complex mix of science, philosophy, and culture. For one, his ideas directly contradicted the prevailing Aristotelian physics, which argued that the heavy, imperfect Earth naturally belonged at the center of the universe. Furthermore, the great astronomer Hipparchus, whose work heavily influenced Ptolemy, championed the geocentric model. Hipparchus's system was incredibly successful at predicting planetary motions, giving it a powerful practical advantage. There was also a strong philosophical and religious aversion to displacing humanity from the center of God's creation. The sheer scale of Aristarchus's universe, with the stars immeasurably far away to explain why we don't see their positions shift as Earth moves, seemed implausible and unsettling to his contemporaries. His vision of the cosmos was simply too vast, too humble for human pride, and too mathematically demanding for an era that favored Earth-centered certainty. His star briefly blazed with an unimaginable light, only to be dimmed by the weight of tradition for nearly 2 millennia. While Aristarchus grappled with the grand architecture of the solar system, his countryman Conon of Samos turned his sharp eyes to a much more personal corner of the heavens. In the 3rd century before the Common Era, Conon served as the court astronomer to Ptolemy III in the magnificent, intellectually buzzing city of Alexandria. His role was a fascinating blend of pure science and royal service, and it was this unique position that led to one of the most charming and enduring legends in all of astronomy. Conon was a respected mathematician, a contemporary and friend of the legendary Archimedes, who himself praised Conon's work on conic sections, but his daily duties extended far beyond abstract geometry. He was a meticulous observer of the sky, and he applied his knowledge to very practical problems. Ancient historians like Pliny the Elder credit him with developing a form of astrometeorology, creating a star-based calendar that predicted weather patterns and the seasonal winds vital for Mediterranean shipping and agriculture. By carefully noting the risings and settings of certain stars and constellations, he could forecast the conditions that would arrive weeks or months later, turning celestial patterns into a practical tool for his kingdom. But his most famous contribution is a story that intertwines royal vanity, divine favor, and scientific opportunism. The tale goes that Queen Berenice II, the wife of Ptolemy III, made a vow to the gods. She promised to sacrifice her beautiful, long hair to the goddess Aphrodite if her husband returned safely from a dangerous military campaign. When Ptolemy did indeed return victorious, the queen, true to her word, cut off her famed locks and placed them in the goddess's temple. The very next day, the offering was gone. To avert a royal crisis and potential divine wrath, the quick-thinking Conon provided a brilliant explanation. He announced that the gods had been so pleased with the queen's sacrifice that they had placed her hair among the stars for all eternity. He pointed to a faint, misty cluster of stars near the tail of the constellation Leo and declared it to be the new constellation Coma Berenice's, or Berenice's hair. This was more than just clever flattery. It was a genuine astronomical discovery. That dim cluster of stars had not been formally identified as a distinct constellation before. While Conon may not have been the first person to ever see it, he was the first to catalogue it, name it, and weave it into the official celestial map. His act secured his place in the royal court's good graces, and more importantly, it left a permanent mark on our night sky. To this day, Coma Berenice's remains a recognized constellation, a testament to a clever astronomer who knew how to use his science to solve a very earthly problem. It stands as a beautiful reminder that the history of astronomy isn't just about cold calculation. It's also deeply human, filled with stories of loyalty, love, and the desire to leave a lasting impression, whether on a kingdom or in the cosmos themselves. Now, let's journey from the courtly legends of Conon to the rigorous, data-driven world of a true scientific pioneer, Timocharis of Alexandria. In the early 3rd century before the Common Era, as the city of Alexandria was blossoming into the intellectual capital of the world, Timocharis and his colleague Aristyllus were engaged in a project of breathtaking ambition. They weren't just observing the stars, they were attempting to systematically map the entire heavens, creating one of the first comprehensive star catalogues in Western history. This was astronomy moving from storytelling and weather prediction into the realm of hard, quantifiable data. Their most monumental achievement was the establishment of what many historians consider the first dedicated scientific observatory. Imagine the scene, a building or perhaps a series of platforms equipped with the finest astronomical instruments of the age dioptra for measuring angles, armillary spheres for modeling the celestial sphere, and simple but precise sighting tubes. This wasn't a temple or a royal vanity project, it was a factory for producing knowledge. Night after night, Timocharis and Aristyllus would meticulously record the positions of the brightest stars, noting their celestial coordinates with a level of precision that was unprecedented for their time. They were creating a snapshot of the sky, a fixed baseline against which all future change could be measured. They couldn't have known it, but they were laying down a cornerstone for one of the most profound discoveries in human history. The true, world-altering value of their work would only be revealed a century and a half later, through the brilliance of another astronomical giant, Hipparchus. The story goes that in the year 134 before the Common Era, a brilliant new star, a nova, appeared in the constellation Scorpius. This unexpected event spurred Hipparchus to create his own, more detailed star catalogue to track any future changes. To check his own measurements for accuracy, he naturally turned to the pioneering work of Timocharis and Aristyllus, the best existing data he could find. As he compared their recorded positions of specific stars like Spica, the brightest star in the constellation Virgo, against his own contemporary observations, he noticed something astonishingly subtle yet profoundly significant. The star's position had shifted. It wasn't a large error on the part of the earlier astronomers. It was a consistent, systematic drift. The entire celestial sphere, the fixed backdrop of the universe as everyone understood it, was slowly moving. This was the monumental discovery of the precession of the equinoxes. Hipparchus realized that the Earth's axis itself slowly wobbles over a vast cycle of about 26,000 years, causing the positions of the equinoxes to gradually shift westward against the backdrop of the stars. It was a discovery that redefined humanity's understanding of time and the stability of the cosmos itself, and it was only possible because Timocharis and Aristyllus had provided that crucial first data point. Their catalogue was the before picture in a cosmic before and after comparison that spanned generations. Without their diligent, painstaking recordings, that subtle drift might have gone unnoticed for centuries longer. Timocharis represents the often unseen engine of scientific progress, the meticulous data collector whose work, though it may lack the immediate glamour of a grand theory, becomes the indispensable foundation upon which revolutions are built. He measured the sky so that others could discover it was moving. While Timocharis was a central figure in that first great observatory of Alexandria, he did not work alone. His partner in this colossal undertaking was a man named Aristyllus, and to speak of one is to inevitably speak of the other. Theirs was one of the first great collaborations in the history of science, a partnership that fundamentally changed how humanity interacted with the cosmos. Where earlier astronomical traditions, particularly in Babylon, had been focused on celestial omens and cyclical predictions, Timocharis and Aristyllus embarked on a new kind of quest. They sought to create a precise mathematical map of the sky itself, fixing the positions of the stars in a coordinate system that could be used and built upon by generations to come. Their methodology was groundbreaking. They are widely credited with adapting and formalizing the use of ecliptic coordinates, a system still used by astronomers today. This meant they didn't just note that a star was in a certain constellation. They measured its precise celestial longitude, its position along the path of the sun, and its celestial latitude, its distance north or south of that path. To make these measurements, they relied on and likely refined the premier astronomical instrument of their age, the armillary sphere. This complex device was a model of the celestial sphere, composed of a series of interlocking rings that represented key circles like the equator and the ecliptic. By carefully aligning this instrument and sighting a star through its rings, they could read off its coordinates with remarkable accuracy. Their work transformed the armillary sphere from a theoretical model into a practical tool for data collection. The sheer volume of their work is staggering to consider. Ancient sources suggest their catalogue contained around 850 stars. Each one required multiple observations on different nights to confirm its position, a painstaking process of measurement, recording, and calculation done entirely by hand under the flickering light of oil lamps. This was not a task for a single lifetime, which is why their partnership was so essential. They established a system, a repeatable process for generating reliable data. In doing so, they effectively invented the concept of the scientific observatory as a permanent institution for ongoing research, setting a precedent that would be followed for centuries in Alexandria and beyond. The ultimate testament to their success is not just the catalogue they left behind, but how it was used. Their data became the gold standard for Greek astronomy for over a century. When the brilliant Hipparchus needed a reliable baseline from the past to compare with his own observations, it was the work of Timocharis and Aristyllus he turned to. Their coordinates were the fixed points in time that allowed him to detect the slow, grand wobble of the Earth's axis known as precession. Later, Claudius Ptolemy, whose own work would dominate astronomy for over a millennium, used their star positions as a critical reference and starting point for his monumental Almagest. In a very real sense, the entire edifice of classical astronomy rests upon the foundation they so carefully laid. Aristyllus, often overshadowed even within this partnership, represents the indispensable collaborator, the meticulous, detail-oriented scientist whose commitment to accuracy and precision makes revolutionary discovery possible for others. He was one half of the team that gave astronomy its first reliable map, turning the starry sky from a realm of myth into a domain of measurement. Now, as we move from the grand observatories of Alexandria, our focus shifts to a different kind of foundational mind, one whose work provided the essential mathematical bedrock for everything that followed. In the 4th century before the Common Era, in the city of Pitane in what is now Turkey, a mathematician and astronomer named Autolycus of Pitane was hard at work formalizing the very rules of the celestial game. While the astronomers we've discussed were mapping stars and detecting cosmic motion, Autolycus was doing something equally vital. He was building the rigorous mathematical framework that would allow those observations to make sense. His treatise on the moving sphere holds a unique and critically important title. It is the oldest completely preserved Greek mathematical text in existence. This survival alone tells us something profound about its value to the ancient world. So what exactly is in this ancient book on the moving sphere is not a catalogue of stars or a list of planetary positions. Instead, it is a work of pure spherical astronomy. Autolycus was concerned with the geometry of the heavens, treating the sky as a perfect rotating sphere. He set out to prove a series of theorems about how this sphere moves and how points on its surface behave. For instance, he mathematically demonstrated that a sphere rotating uniformly about its axis will always have the same point as its pole, and that any point on the sphere's surface will describe a circle parallel to the equator. These might sound like abstract geometric exercises, but they were absolutely fundamental. They provided the logical proof that the simplistic model of a two-dimensional dome rotating over a flat Earth was mathematically impossible, thereby firmly establishing the concept of a spherical, rotating cosmos as the only viable model. He was building the instruction manual for the armillary spheres that Timocharis and Aristyllus would later use. His work extended into the practical challenges of observing this rotating sphere from a fixed point on Earth. He explored the phenomenon of stars rising and setting, providing geometric proofs for why certain stars near the celestial poles never dip below the horizon, what we call circumpolar stars, while others are forever hidden from view for a given observer. This had immense practical application. For any ancient navigator or timekeeper, understanding which stars were always visible provided a fixed, unwavering reference point in the night sky. By formalizing this mathematically, Autolycus turned local knowledge into a universal principle. His second surviving work, On Risings and Settings, delves even deeper into this, meticulously classifying the different types of stellar risings and settings throughout the year and providing a predictive model for them. This wasn't just theory, it was a mathematical guidebook for predicting the sky's behavior. The true measure of Autolycus's influence is seen in the generations he directly inspired. He was the teacher of Aristyllus, who would go on to become the head of the Platonic Academy, ensuring that this rigorous mathematical approach to philosophy and science was passed directly into the heart of Greek intellectual life. More importantly, his work formed the essential prerequisite for the monumental achievements of Euclid, who would build upon this foundation of spherical geometry, and later Hipparchus and Ptolemy. When Hipparchus calculated the precession of the equinoxes, he relied on a mathematical understanding of the celestial sphere that Autolycus had helped to codify. When Ptolemy constructed his complex models of planetary motion in the Almagest, the underlying assumptions about spheres and circles in motion all stemmed from this earlier work. Autolycus may not have made a flashy, singular discovery like a new star or a wobbling axis, but he provided the solid ground upon which those discoveries could stand. He gave astronomers the mathematical language to describe the cosmos, transforming observation into a precise and predictive science. Yet for all its elegance, the system had its flaws. The complex interplay of all these spinning spheres still couldn't perfectly replicate the observed motions of the planets, particularly their puzzling retrograde loops where they appear to temporarily reverse course in the night sky. It was here that a brilliant student of Eudoxus, Callippus of Samos, stepped in during the 4th century before the Common Era. Callippus wasn't there to tear down his teacher's model, he was there to perfect it. He recognized the system's potential and sought to refine its mathematical precision, adding a new layer of complexity to bring the model closer to the reality of the heavens. Callippus's most significant contribution was the addition of 7 new spheres to Eudoxus's original 27. He looked at the data and realized that certain celestial motions were still not being accurately represented. To account for these discrepancies, he introduced a second set of spheres for both the Sun and the Moon. For the Sun, this helped to better model the slight variations in the length of the seasons. For the Moon, it was crucial for explaining the subtle changes in its speed and the slight wobbles in its orbit that affect eclipses. He also added 1 extra sphere each for Mercury, Venus, and Mars, the planets whose motions were the most difficult to predict. This wasn't just tinkering, it was a deliberate, calculated upgrade. By increasing the total number of spheres to 34, Callippus created a far more robust and accurate predictive machine, pushing mathematical astronomy a significant step closer to a true physical model of the cosmos. His genius, however, wasn't confined to planetary theory. Callippus also turned his attention to one of the most practical problems of the ancient world, calendar keeping. He sought to improve upon the famous 19-year Metonic cycle, which laid out a pattern where solar years and lunar months realign. While Meton's cycle was a monumental achievement, it was slightly off by about half a day every 19 years. Over centuries, this small error would accumulate, throwing seasonal markers out of sync. Callippus devised a brilliant correction. He proposed a grander cycle spanning 76 years, which is exactly 4 Metonic cycles. By taking that 4-cycle block and deducting 1 single day from it, he effectively reset the error. This Calippic cycle, as it came to be known, was a staggering leap in accuracy. It meant that over a span of nearly a millennium, his calendar would stay in near-perfect harmony with the actual Sun and Moon, a feat of long-term mathematical planning that was virtually unmatched in the ancient world. Callippus's work reached its widest audience through his collaboration with the great philosopher Aristotle. When Aristotle was developing his own cosmological views, he didn't start from scratch. He built directly upon the mathematical models of Eudoxus and Callippus. In his seminal work, Metaphysics, Aristotle describes and praises Callippus's modifications, adopting the 34-sphere system as the most advanced physical description of the universe available. For Aristotle, these nested, rotating crystalline spheres were not just mathematical fictions. They were actual, physical components of the cosmos, and Callippus's refinements made this physical model more plausible. This partnership between philosopher and mathematical astronomer was crucial. It cemented the concentric sphere model as the dominant cosmological theory for centuries to come, blending precise observation with a comprehensive vision of how the universe must be constructed. Callippus represents a pivotal moment in science, the meticulous improver whose careful adjustments to a grand theory ensure its survival and elevate it to a new height of influence, proving that progress often comes not from revolution, but from thoughtful, precise refinement. Now we turn our gaze to a much earlier and more foundational figure, a bridge between the mystical astronomy of the ancient Near East and the burgeoning rationalism of early Greece. In the 6th century before the Common Era, on the small island of Tenedos just off the coast of Troy, an astronomer named Cleostratus was at work. His name may not ring with the fame of later Greek thinkers, but his contributions were absolutely vital, for he is widely credited with introducing a concept so fundamental we still use it today, the zodiac. Imagine the Greek understanding of the sky before his time. The constellations were largely a collection of disparate myths, heroes, animals, and objects scattered across the heavens with no unifying structure. Cleostratus looked at this celestial tapestry and saw a pattern, a grand highway along which the sun, moon, and planets traveled. He divided this path, which we call the ecliptic, into 12 equal sections of 30 degrees each section named for the constellation that resided within it. This was the birth of the zodiacal system in Greek thought. He almost certainly did not invent this idea out of nothing. The Babylonians, with their centuries of meticulous celestial record-keeping, had already established their own version of the zodiac. Cleostratus, living in a region that was a crossroads of trade and culture between Greece and the East, was perfectly positioned to encounter this advanced Babylonian knowledge. His genius was not in invention, but in translation and adaptation. He took this sophisticated foreign system and grafted it onto the existing body of Greek star lore, creating a hybrid framework that was both mathematically useful and culturally familiar to his people. He replaced or reinterpreted Babylonian constellations with Greek equivalents, perhaps the Babylonian Emuel. A pin became the Greek archer, Sagittarius. This act of cultural synthesis was arguably more important than a pure discovery. It gave Greek astronomy a powerful new organizing principle, a coordinate system that would underpin all their future observations and theories. But Cleostratus was far more than just an importer of ideas. He was a sharp observer in his own right, particularly focused on what are known as the phases of the stars. In ancient astronomy, a star's phase referred to its annual cycle of becoming visible just before sunrise or just after sunset, events that were critically important for marking the changing seasons. Cleostratus is said to have made important observations of the pre-dawn risings of the constellations Sagittarius and Arcturus, using these celestial events as fixed points in the year. This wasn't just stargazing, it was practical science. By carefully noting these annual markers, he could create a far more reliable calendar tied directly to the immutable motions of the cosmos, rather than the flawed and drifting lunar calendars of the past. His work on calendar reform was perhaps his most immediate and impactful contribution to daily life. The Greek calendars of his time were a messy affair, often out of sync with the solar year and requiring frequent, arbitrary adjustments by officials. Cleostratus proposed an 8-year cycle, known as an octiteris, to better harmonize the lunar months with the solar year. This cycle aimed to ensure that seasonal festivals would always fall in the correct season, which was crucial for an agricultural society. While his 8-year cycle was later refined by Meton's more famous 19-year cycle, it represented a crucial step forward. It was an attempt to replace political guesswork with astronomical certainty, to ground human timekeeping in the reliable rhythms of the universe. Cleostratus of Tenedos stands as a pivotal figure in the dawn of Western science, a practical observer who helped transform the Greek sky from a realm of story into a grid of measurement, setting the stage for all the astronomical genius that would follow in his wake. Now we come to a thinker whose ambition was nothing short of celestial, a man who attempted to build a model of the entire cosmos using nothing but geometry and pure reason. In the 4th century before the Common Era, Eudoxus of Samos, a mathematician and astronomer of prodigious talent, looked at the chaotic dance of the planets and saw not confusion, but a hidden harmony waiting to be unlocked. The prevailing view of the universe was still deeply mythological, a place where gods drove chariots across the sky. Eudoxus proposed something radically different and breathtakingly modern, a universe governed by mathematical law. His masterwork was the first comprehensive mathematical model of the cosmos, a system of 27 nested, transparent spheres, all centered on the Earth. Each planet, the Sun and Moon included, was assigned its own set of these rotating spheres. The innermost sphere for a planet carried the celestial body itself, while the outer spheres, each rotating on a different axis and at a different speed, combined their motions to produce the complex path observed from Earth. This was his ingenious solution to the most baffling problem in ancient astronomy: retrograde motion. Planets normally drift slowly eastward against the backdrop of stars, but periodically they appear to halt, reverse course for a few weeks in a westward loop, then resume their original path. To the Greeks, this was deeply unsettling, a violation of the perfect, uniform circular motion they believed governed the heavens. Eudoxus's spheres showed how this apparent irregularity could be the result of multiple, perfect, uniform motions combined. It was a work of sheer geometric genius, an attempt to save the phenomena to explain the messy observations of the real world through the pristine beauty of mathematical ideal. But Eudoxus was far more than a theoretical model builder. He was also a meticulous observer. He established an observatory in his hometown of Cnidus, and from there he painstakingly charted the stars. His work, The Phenomena, was a foundational text that systematically described the constellations and the celestial sphere. It wasn't just a list of star patterns, it was a guide to the heavens, intended for both practical use and philosophical contemplation. He described the rising and setting of constellations, providing a celestial calendar that could be used for navigation and marking the seasons. This work was so influential that it was later versified by the poet Aristyllus, spreading Eudoxus's descriptions of the sky throughout the Hellenistic world and ensuring his star lore became the standard for generations. His influence on the giants of Greek philosophy cannot be overstated. He studied at Plato's academy, and it's said that his planetary model was a direct response to Plato's famous challenge to his students to find the uniform and ordered motions that could explain the apparent wanderings of the planets. In answering this call, Eudoxus provided the mathematical backbone for Plato's entire cosmological vision. Later, Aristotle would adopt Eudoxus's model, though he made a critical alteration. For Eudoxus, the spheres were likely a mathematical device, a calculating tool. Aristotle, however, interpreted them as physical, crystalline realities, and he had to add even more spheres to prevent the motion of one planet from interfering with another. This Aristotelian version of the Eudoxian system became the dominant cosmological view for nearly 2,000 years. Eudoxus of Cnidus represents a pivotal moment in human thought, the point where astronomy truly became a mathematical science. He dared to believe that the universe could be understood not through myth, but through geometry, setting a precedent for every mathematical astronomer who would follow, from Copernicus to Newton. While Eudoxus was weaving his celestial spheres and Callippus was refining them, a different kind of practical challenge was being solved in the heart of Athens. In the bustling agora, the central public space, an astronomer named Meton made a public installation in the 5th century before the Common Era that would change how an entire civilization marked time. His contribution wasn't a grand cosmic model, but something far more immediate, a reliable calendar. The problem he faced was one of the oldest and most persistent in human history, the frustrating mismatch between the cycles of the sun and the moon. A lunar month is about 29.5 days, making a lunar year roughly 354 days. A solar year, the time it takes for the seasons to complete their cycle, is about 365.25 days. This 11-day gap might not seem like much, but it adds up quickly. A festival meant to celebrate the autumn harvest would, under a purely lunar calendar, slowly drift into the heat of summer over just a few years. Meton's brilliant solution was a cycle of 19 years. He discovered that after this period, the phases of the moon will recur on the same dates of the solar year. In essence, 19 solar years almost exactly equals 235 lunar months. This means that if you can devise a calendar that inserts 7 extra months into those 19 years, the lunar and solar cycles will harmonize beautifully. This 19-year cycle, which now bears his name, the Metonic cycle, was a staggering leap in accuracy. It wasn't a perfect alignment, drifting by about 2 hours every cycle, but for the ancient world, it was the most precise long-term calendar tool ever developed. It allowed for the prediction of lunar phases and eclipses with remarkable reliability over a time span that could be planned for generations. To make this complex system tangible for the citizens of Athens, Meton didn't just publish a paper, he erected a public monument to time itself. On the Phoenix Hill, he installed a parapegma. This was not a simple sundial but an elaborate astronomical calendar, likely a stone slab with a series of holes next to inscribed astronomical and meteorological information. Each day, a peg would be moved to the next hole, tracking the progression of the year. But the true genius of the parapegma was its annotations. It would note the predicted rising and setting of key stars and constellations, the expected changes in weather, and the direction of the seasonal winds. It transformed the abstract Metonic cycle into a daily, practical guide for farmers, merchants, and sailors, connecting the grand celestial cycles to the rhythm of daily life in Attica. Meton's work was deeply grounded in meticulous observation. Ancient sources describe how he began his calculations from the summer solstice in the year 432 before the Common Era, using a specialized device called a heliotropion to pinpoint the exact moment the sun reached its northernmost point. This commitment to empirical data collection places him firmly at the crossroads of tradition and the emerging scientific spirit of inquiry. While his cycle was likely built upon even earlier Babylonian knowledge, as they too had discovered this 19-year pattern, Meton's true legacy was his public application of it. He integrated this advanced astronomical knowledge into the very fabric of Athenian society, making celestial order a part of civic life. His parapegma became the model for countless others throughout the Greek world, and his Metonic cycle became a fundamental pillar of later calendars, including the one used by the great astronomer Ptolemy, and centuries later, forming the basis for the calculation of Easter in the Christian ecclesiastical calendar. Meton of Athens represents the power of applied astronomy, taking a beautiful mathematical truth about the heavens and using it to bring order and predictability to the human world below. While Eudoxus was constructing his cosmic spheres and Meton was refining his calendar in Athens, another brilliant mind from the island of Chios was making a discovery so fundamental it shapes our very understanding of the seasons. In the 5th century before the Common Era, Oenopides of Chios turned his attention to a single, critical angle, the tilt of the Earth's axis relative to its path around the Sun. This angle, which we now call the obliquity of the ecliptic, is the reason we have summer and winter. It dictates how directly the Sun's rays strike different parts of the globe throughout the year. Before Oenopides, this was likely an unmeasured assumption. He was the first to not only recognize its importance but to actually calculate its value. Using the meticulous tools of Greek geometry and careful observation, he determined this angle to be 24 degrees. While we now know the precise value is closer to 23.4 degrees and slowly varies over millennia, his measurement was astonishingly accurate for his time. This wasn't just a number, it was a profound insight into the very architecture of our planet's relationship with the Sun, providing a physical, geometric reason for the changing seasons that was far more scientific than any mythological explanation. But Oenopides was not content with just measuring the Earth's lean. He also sought to bring order to the complex dance between the Sun and the Moon. He identified what is known as the Great Year, a period of 59 years. His genius was in recognizing that this span represented a near-perfect reconciliation of the solar and lunar cycles. Within this 59-year period, the phases of the Moon and the position of the Sun would realign almost exactly. This was a significant refinement of earlier calendrical cycles, offering a longer and more accurate framework for predicting celestial events and keeping lunar calendars in sync with the solar year. This 59-year cycle became a valuable tool for astronomers who came after him, providing a reliable long-term clock for the heavens. His contributions extended beyond pure observation into the realm of mathematical problem-solving. Oenopides is credited with solving two classic geometric challenges using only a straight edge and a compass, the approved tools of Greek geometry. He found a way to draw a line from a point outside a circle that touches it at just one point, what we call a tangent. He also solved the problem of creating an angle equal to a given angle but positioned at a specific point on a line. These might seem like abstract exercises, but in the hands of an astronomer, they were powerful practical tools. The ability to work with tangents and angles is the very foundation of calculating celestial positions, distances, and movements. By formalizing these geometric techniques, Oenopides was effectively building the essential toolkit that would allow future astronomers to map the cosmos with ever greater precision. The true measure of Oenopides' intellect lies in the company he kept and the influence he wielded. He was a contemporary and respected peer of the great philosopher Anaxagoras, and his ideas clearly influenced the mathematical genius of Plato. In his dialogue Epinomis, Plato discusses astronomical cycles and the obliquity of the ecliptic, concepts that Oenopides had pioneered. He represented a crucial shift in thinking, moving away from purely philosophical speculation about the cosmos and towards a methodology grounded in geometry, calculation, and empirical measurement. He stood at a pivotal crossroads, blending the Ionian tradition of inquiry with the rigorous, proof-based approach that would define Greek mathematics. Oenopides of Chios may not have left behind a vast body of written work, but the concepts he quantified, the tilt of our world and the great cycles of time, are etched permanently into the foundation of astronomy, providing the first clear geometric rules for the cosmic clockwork we observe every day. Among the brilliant yet often overlooked minds of the ancient world, few proposed a cosmology as radical and as strangely prescient as Philolaus of Croton. In the 5th century before the Common Era, this Pythagorean philosopher shattered the most fundamental assumption of his time, that the Earth sat motionless at the absolute center of the universe. His model was a breathtaking leap of imagination, born from the Pythagorean belief that number and harmony were the underlying principles of all reality. He didn't just tweak the existing system, he completely re-envisioned our place within it, proposing that the Earth, along with all the other celestial bodies, was in constant motion around a central point. But this center was not the sun, as we might expect. At the heart of his cosmos burned a magnificent, unseen, central fire, which he called the hearth of the universe, the divine source of all light and heat. In this stunningly original system, 10 celestial bodies danced in perfect harmony around this central flame. Their number was no accident. 10 was considered by the Pythagoreans to be the perfect number, the symbol of completeness. The visible universe, as Philolaus described it, was arranged in a series of concentric circles. Closest to the central fire was a mysterious, counterintuitive body he called the counter-Earth, or Antichthon. Beyond that, in order, revolved our own Earth, the Moon, the Sun, the 5 known planets Mercury, Venus, Mars, Jupiter, and Saturn, and finally, the outermost sphere of the fixed stars. This arrangement solved a vexing observational problem for the Greeks, why they could never see the central fire or the counter-Earth. Philolaus reasoned that the inhabited part of the Earth, the known world of Greece and the Mediterranean, was forever turned away from the center, perpetually facing outwards into the cosmos. We were like spectators on the outer rim of a carousel, always looking away from the central motor that powered the entire ride. The role of the counter-Earth within this model is particularly fascinating. It wasn't merely a fantastical addition. It served a crucial purpose in completing the Pythagorean perfect number of 10 celestial bodies, but it also had a more practical, albeit speculative, function. Some interpretations suggest it was thought to act as a shield, protecting our part of the world from the immense, potentially destructive heat of the central fire. Others propose it was necessary to explain certain lunar eclipses, its unseen presence accounting for phenomena that otherwise seemed inexplicable. This ingenious, if incorrect, solution highlights a key aspect of Pythagorean astronomy. A powerful desire for mathematical elegance and symmetry sometimes took precedence over pure observational evidence. The model had to be beautiful and numerically perfect, even if it required inventing an entire unseen world to make the numbers add up. The true brilliance and lasting influence of Philolaus's cosmology, however, lies not in its specifics but in its revolutionary core principle. For the first time in Western thought, the Earth was dethroned. It was no longer the static, immovable center of all creation but a moving body, a planet in the truest sense of the word, which means wanderer. This single, profound idea was a necessary precursor to all future heliocentric theories. It broke the psychological and philosophical barrier that had kept the Earth firmly anchored at the center for centuries. While his central fire was not the sun, the structural similarity is undeniable. He had envisioned a sun-centered system in all but name. The sun, in his model, was demoted from a god-driven chariot to a glass-like body that merely reflected the light of the central fire outwards to illuminate the cosmos, but the crucial motion was still there. We know of Philolaus's ideas primarily through the later writings of Aristotle, who criticized the model for its perceived absurdities, particularly the counter-Earth. Yet, despite this criticism, the seed had been planted. It is highly probable that a young, curious Aristarchus of Samos, the man who would later propose a true heliocentric model with the sun at the center, was profoundly influenced by the work of Philolaus. He took the revolutionary idea of a moving Earth and simply replaced the central fire with the sun, creating a far more accurate and elegant system. Philolaus of Croton, therefore, stands as a monumental figure in the history of science. He was the first to dare suggest that the familiar ground beneath our feet was not the center of everything, but a participant in a vast celestial dance governed by the beautiful, unchanging laws of mathematics. While the Pythagoreans, like Philolaus, were contemplating the grand, harmonious motions of celestial spheres, another brilliant mind was focused on the essential mathematics needed to actually map those motions onto the observable sky. In the 2nd century before the Common Era, a mathematician and astronomer from Bithynia named Theodosius set out to provide astronomers with the indispensable geometric rulebook for a spherical universe. His masterwork, simply titled Spherix, didn't catalogue stars or predict planetary positions. Instead, it did something far more foundational. It rigorously established the core principles of spherical geometry, the very language required to describe the heavens accurately. Imagine the challenge facing ancient astronomers. They had accepted that the Earth and the cosmos were spherical, but how does one actually navigate on the surface of a sphere? The flat plane geometry of Euclid, which was excellent for measuring fields and building structures, was utterly useless for tracing the path of a star across a curved sky. Theodosius's Spherix was the direct answer to this problem. It is often described as the spherical equivalent of Euclid's Elements, a systematic compilation of definitions, axioms, and proofs, but for the surface of a sphere. He defined the key concepts. A spherical triangle is formed by the arcs of great circles, and its angles, unlike those on a flat plane, can add up to more than 180 degrees. He proved complex theorems about the relationships between these angles and arcs, providing the necessary tools to calculate distances and positions on the celestial sphere. This was not an abstract academic exercise. Every single observation made by an ancient astronomer, the rising of a constellation, the altitude of the sun at noon, the position of a planet, was a measurement on the inside surface of an imaginary sphere. Theodosius gave them the mathematical machinery to work with those measurements. For instance, his work allowed an observer to calculate the length of daylight for any given day of the year at any latitude, a critical piece of information for agriculture, navigation, and timekeeping. It provided the geometric basis for designing the most important astronomical instrument of the age, the astrolabe. Without the theorems proven in Spherix, the sophisticated models of Hipparchus and the predictive tables of Ptolemy would have been mathematically impossible. Theodosius was building the scaffolding upon which all practical astronomy would be constructed. His contributions extended beyond pure geometry into a revolutionary technique for representing the spherical heavens on a flat surface. Theodosius is credited with pioneering the early principles of stereographic projection. This complex method allows a cartographer to project points from the surface of a sphere onto a flat plane, like mapping the entire night sky onto a single circular sheet. The most common application was projecting the celestial sphere onto the plane of the equator. This was the fundamental operating principle behind the planispheric astrolabe, an instrument that would become the astronomer's quintessential tool for over a millennium. By working out the geometric laws of this projection, Theodosius enabled the creation of these portable, analog computers of the sky, which could solve problems of time, latitude, and stellar positions with a simple rotation of a metal plate. What makes Theodosius's work so enduring is its timeless utility. While many astronomical theories were eventually superseded, the geocentric model giving way to heliocentrism, crystalline spheres giving way to orbital mechanics, the spherical geometry laid out in spherics remained permanently true and useful. His proofs were as valid for Copernicus and Kepler as they were for Ptolemy. The book was translated into Arabic during the Islamic Golden Age, where it was studied and revered by scholars who refined the astrolabe to its peak of perfection. Centuries later, it was translated into Latin and became a standard textbook in European universities during the Renaissance, directly aiding the very astronomers who would eventually overturn the ancient cosmos it was originally designed to describe. Theodosius of Bithynia exemplifies a profound truth in the history of science. Sometimes the most revolutionary figure is not the one who proposes a grand new theory, but the one who provides the flawless, timeless tools that make all future theories, both right and wrong, even possible to conceive. While the models of Eudoxus and Callippus sought to explain planetary motion with nested spheres, their systems were incredibly complex and still struggled with precise prediction. Enter Apollonius of Perga, a mathematical genius of the 3rd century before the Common Era, who approached the problem not with physical spheres but with pure, elegant geometry. He is a classic example of a forgotten founder. Though his name is less known than Ptolemy's, his revolutionary ideas became the very engine that powered the dominant model of the universe for over 1,000 years. His monumental contribution was the development of two simple yet profoundly powerful geometric devices, the epicycle and the deferent. To understand his breakthrough, picture a celestial whirligig. Apollonius proposed that a planet like Mars does not travel on a simple circle around the Earth. Instead, it moves on a small circle called an epicycle, whose center itself is carried along a larger circle centered on the Earth, known as the deferent. The planet whirls around on its little epicycle while simultaneously being carried around the big deferent. This simple combination of two circular motions was nothing short of genius. It provided a beautifully geometric solution to the most perplexing problem in the sky, retrograde motion. Normally, a planet moves steadily eastward. But during its retrograde loop, it appears to reverse course. In Apollonius's model, this happens naturally when the planet is on the inner part of its epicycle circle, moving in a direction opposite to the motion of the epicycle center along the deferent. From our earthly viewpoint, this creates the illusion of the planet slowing down, backing up, and then moving forward again. It was a geometric magic trick that saved the phenomena with breathtaking simplicity, replacing a cumbersome system of 27 spheres with a far more flexible and calculable model. But planetary motion was not his only conquest. Apollonius earned his title, the Great Geometer, for his foundational work on conic sections. In his seminal treatise, simply titled Conics, he systematically explored the curves formed when a plane slices through a cone at different angles: the circle, the ellipse, the parabola, and the hyperbola. Before Apollonius, these were seen as abstract curiosities. He was the first to give them the names we still use today and to thoroughly investigate their properties through rigorous geometric proofs. He defined them not just as slices of a cone, but by their intrinsic geometric properties, such as a parabola being the set of points equidistant from a fixed point and a fixed line. This work was so advanced that it would be nearly 2,000 years before Johannes Kepler realized that an ellipse, not a circle, was the true path of a planet around the Sun. Apollonius had already provided the complete mathematical description of that very curve centuries before it was needed. His conics was a work of pure mathematics so far ahead of its time that its full practical application to physics and astronomy had to wait for the scientific revolution. The ultimate testament to Apollonius's brilliance is the fact that his geometric tools became the indispensable core of the most influential astronomical work in history. When Claudius Ptolemy set out to write the Almagest in the 2nd century of the Common Era, creating a comprehensive mathematical model of the universe, he did not start from scratch. He built his entire system upon the foundation laid by Apollonius. Ptolemy adopted the epicycle and deferent model wholesale, though he added his own refinements like the equant point to better match the observed speeds of the planets. But the basic architecture was pure Apollonius. It was this model, perfected by Ptolemy, that would dominate Western and Islamic astronomy for the next 14 centuries, providing accurate enough predictions to satisfy observers until the time of Copernicus. It is a profound irony of history that the geometric tools created by Apollonius, a man who argued for a heliocentric model, according to some ancient sources, became the very machinery used to uphold the geocentric worldview for over a millennium. His relative obscurity today, compared to the fame of Ptolemy, underscores a recurring theme in the history of science. The innovator who provides the key is often forgotten, while the person who successfully integrates that key into a larger system receives the lasting acclaim. Apollonius of Perga was the architect, and Ptolemy the master builder who used his blueprints to construct an edifice that would stand for ages. Now, let's turn to a figure who acted as one of antiquity's great teachers and compilers, a man whose work became a bridge across which classical astronomy passed to future generations. In the 1st century before the Common Era, on the island of Rhodes, an astronomer and mathematician named Geminus set out to do something remarkably ambitious. He aimed to create a single, accessible volume that would summarize the entire body of Greek astronomical knowledge up to his time. The result was his masterpiece, The Introduction to the Phenomena, a work that stands as one of the clearest and most comprehensive textbooks to survive from the ancient world. Unlike the dense mathematical proofs of Apollonius or the complex models of Hipparchus, Geminus's goal was explanation and synthesis. He wanted to make the cosmos understandable, not just to fellow experts, but to any educated person with a curious mind. His book covered the entire celestial landscape, beginning with a detailed explanation of the zodiac and the path of the sun, moon, and planets. But Geminus went far beyond simple description. He was deeply interested in the practical application of this knowledge, particularly in the field of astrometeorology, the art of predicting weather through the stars. He meticulously documented which constellations, upon their first pre-dawn rising or evening setting, were traditionally associated with the arrival of seasonal rains, the shifting of winds, or the onset of fair weather. For a society deeply dependent on agriculture and maritime trade, this was not abstract science. It was vital, life-saving information. A farmer planting his crops or a ship's captain planning a voyage across the Mediterranean could consult the rhythms Geminus described, using the heavens as a vast, reliable calendar and weather forecast. Perhaps most fascinatingly, Geminus displayed a strikingly modern and critical scientific spirit when it came to the topic of astrology. In his time, the line between astronomy, the study of celestial motions, and astrology, the belief that those motions influence human affairs, was often blurred. But Geminus drew a sharp and clear distinction between them. He ruthlessly critiqued the foundational principles of astrology, pointing out a fundamental logical flaw. He argued that while astrologers claimed a person's fate was set by the precise configuration of the stars at their birth, individuals born at the same moment across different regions, in Greece, Egypt, or Persia, would have vastly different lives and destinies. How could the same celestial alignment produce a king in one land and a slave in another? He saw astrology as a baseless, superstitious practice, utterly separate from the rigorous mathematical science of astronomy. This early advocacy for a clear demarcation between science and pseudoscience is a powerful testament to his rationalist mindset. Geminus's true, enduring value lies in his role as a preserver. His introduction to the phenomena is a treasure trove of quotations, summaries, and explanations of the works of earlier astronomers whose own writings have been completely lost to time. Through Geminus, we hear the echoes of thinkers like Hipparchus, Eudoxus, and the Babylonian scholars whose data the Greeks relied upon. He provides us with crucial insights into their methods, their debates, and their discoveries. He is our window into a world of knowledge that would otherwise be almost entirely dark. In a very real sense, Geminus of Rhodes was the great librarian of the heavens, carefully organizing and cataloging the achievements of his predecessors to ensure they would not be forgotten. He may not have been the most original theorist of his age, but his contribution as a synthesizer and educator was arguably just as important, for he ensured that the lamp of astronomical knowledge, once lit, would continue to burn brightly for the scholars who would follow. Now, as we continue our journey through the great library of the heavens, we arrive at a figure whose contribution is so fundamental that we still use it every single day, though we rarely know his name. In the 2nd century before the Common Era, in the vibrant intellectual hub of Alexandria, an astronomer and mathematician named Hypsicles took on a deceptively simple task: how to measure the sky itself. His solution was to impose a brilliant, human-made order upon the infinite canvas of the cosmos, and in doing so, he gave us a system of measurement that has endured for over 2,000 years. He is the man who formally divided the circle, and thus the celestial sphere, into 360 equal degrees. Before Hypsicles, Greek astronomers used a variety of methods to describe positions, often relying on cumbersome fractions or simply noting that a star rose alongside a certain part of a temple. Hypsicles looked at this inconsistency and saw the need for a universal mathematical standard. He didn't invent the concept of the 360-degree circle out of thin air. He was almost certainly inspired by the ancient sexagesimal, or base 60, numerical system of the Babylonians, which they used for both mathematics and astronomy. But his genius was in recognizing the perfect utility of this system for astronomy and formally adopting and advocating for it within the Greek scientific tradition. The number 360 is a mathematician's dream. It is divisible by a vast number of integers, making calculations of fractions and arcs incredibly smooth and efficient. By applying this division to the ecliptic, the sun's path through the zodiac, he provided every astronomer who followed him with a precise, shared language for celestial longitude. His most significant surviving work, On the Ascension of Stars, showcases this systematic approach in action. This was not a theoretical text but a practical manual for calculating the amount of time it takes for each sign of the zodiac to rise above the horizon at different latitudes. This might sound like an obscure problem, but it was absolutely critical for telling time at night. The rising of constellations was one of the primary ways the ancient world measured the hours after sunset. Hypsicles realized that because the zodiac is tilted relative to the celestial equator, each of its 12 signs takes a different amount of time to rise, depending on the observer's location on Earth. Near the equator, they rise more uniformly, but for someone in Greece or Egypt, the difference is significant. Hypsicles tackled this problem with pure geometry. He calculated the rising times for each zodiac sign for a specific latitude, likely that of Alexandria, creating a set of tables that could be used as a reference. His method involved dividing each sign, which spans 30 degrees of the 360-degree circle, into smaller arcs and then using spherical geometry to compute their ascension. This work was a monumental step forward in spherical astronomy, providing a mathematical recipe that could be adapted for any location on Earth. It transformed timekeeping from a matter of rough estimation into a calculable science. A navigator or a priest could now determine the hour of the night with far greater accuracy by observing which degree of which zodiac sign was crossing the eastern horizon. The influence of Hypsicles' work rippled far beyond the shores of the Mediterranean. His rigorous quantitative approach, especially his use of the 360-degree system, became the gold standard for all subsequent Hellenistic astronomy. It was seamlessly integrated into the work of the great Claudius Ptolemy, whose Almagest used this very system to map over 1,000 stars. But perhaps his greatest legacy was how his ideas were carried forward and refined during the Islamic Golden Age. Islamic astronomers who placed a supreme value on precision for timekeeping for prayer and for navigation across vast deserts and seas seized upon Hypsicles' methods. Scholars like Habash al-Hazib and al-Batani expanded his calculations of ascensional differences, creating more detailed tables for many different latitudes. The 360-degree circle became, and remains, the unchallenged foundation of all angular measurement in astronomy, geography, and navigation. Hypsicles of Alexandria exemplifies a profound truth in the history of science. Sometimes the most revolutionary innovation is not a new theory about what things are, but a better, more precise tool for measuring them. He gave us the ruler we still use to measure the universe. While Hypsicles was perfecting the tools to measure the heavens with his 360-degree circle, another Alexandrian scholar was about to apply astronomical precision to a problem of immense earthly importance, the chaos of the Roman calendar. In the 1st century before the Common Era, Sosigenes of Alexandria was a respected astronomer and philosopher whose name would become permanently etched into the very fabric of Western timekeeping. His story begins not in a secluded observatory, but at the crossroads of immense political power and advanced scientific knowledge. The Roman calendar, by the time of Julius Caesar, was in a state of disastrous disarray. It was a convoluted lunar system that had drifted so far out of sync with the solar year that the harvest festival was occurring in the dead of winter. Caesar, fresh from his campaigns in Egypt, recognized this administrative nightmare. While in Alexandria, he witnessed the far superior Egyptian solar calendar, a system that had maintained its seasonal alignment for centuries. Needing an expert to overhaul Rome's timekeeping, he turned to the finest scientific mind he could find, Sosigenes. Sosigenes' primary task was to calculate the true length of the tropical solar year, the time it takes for the sun to return to the same position in the cycle of seasons. Drawing upon centuries of Egyptian astronomical records, which were the most extensive and accurate in the ancient world, he determined this length to be 365¼ days. His genius, however, lay not in the measurement itself, but in its practical application. He proposed a brilliantly simple solution, a calendar of 365 days, with an extra day added every 4th year to account for that accumulated quarter day. This was the birth of the leap year, and the resulting Julian calendar was a masterpiece of pragmatic design. It discarded the messy, politically manipulated lunar months of the old Roman system in favor of a clean, predictable solar structure with months of fixed length. When Caesar implemented this new calendar in 45 before the Common Era, he had to insert an extraordinary 90 days into the year to realign the seasons, a period known as the last year of confusion. From that point forward, the Western world had a stable, scientific way to mark the passage of the years. Beyond his role as a calendar reformer, Sosigenes was also a sharp critical thinker. From fragments of his work and references by later commentators, we learn that he was a vocal critic of Aristotle's astronomy. This was a bold stance, as Aristotle's authority was immense. Sosigenes took particular issue with Aristotle's complex system of 55 concentric celestial spheres, which were intended to physically explain the motions of the planets. Sosigenes pointed out a fundamental flaw. This model failed to account for the well-documented variations in planetary brightness. If the planets were all fixed on nested spheres centered on the Earth, their distance from us would never change, and thus their brightness should remain constant. Yet observers could clearly see that Mars and Venus, for instance, grew significantly brighter and dimmer over time, proving their distance from Earth was variable. This was a serious empirical challenge that Aristotle's model could not answer. Sosigenes' criticism highlights a shift towards an astronomy grounded in observational evidence rather than pure philosophical deduction, signaling a more modern scientific attitude. The legacy of Sosigenes of Alexandria is one of enduring, tangible impact. The Julian calendar he designed for Caesar proved to be remarkably accurate. While the tiny discrepancy of 11 minutes per year between his calculation and the true solar year would eventually cause a drift of about 10 days by the 16th century, its stability was unprecedented. It governed the Western world for over 1,600 years, forming the bedrock upon which our modern Gregorian calendar was built. Every time we note a date, we are operating within a system whose fundamental architecture was laid down by this Alexandrian astronomer. His work demonstrates the profound power of applying precise celestial knowledge to human civilization, turning the abstract motions of the heavens into the reliable rhythm of days, years, and history itself. He was the perfect fusion of scholar and advisor, a man who used his understanding of the cosmos to bring order to the world below. While Sosigenes was bringing order to the Roman calendar, another meticulous observer was busy creating a more precise map of the stars themselves. In the 1st century of the Common Era, a Greek astronomer named Agrippa, who hailed from Bithynia in what is now northern Turkey, made a specific observation that has allowed his name to echo through the ages. He witnessed and recorded a delicate celestial event, the moment the moon passed directly in front of the star cluster known as the Pleiades, blotting out its shimmering light in what astronomers call an occultation. This was more than just a beautiful sight, it was a critical data point. By carefully noting the exact time and position of this event, Agrippa provided future astronomers with a verifiable anchor in time, a fixed moment against which other observations could be compared and calibrated. This single act of precise observation typifies his approach to the science, a commitment to empirical data and careful measurement. Agrippa's most significant work was his own star catalogue, a systematic effort to record the positions of the celestial bodies with unprecedented accuracy. Building on the tradition of Hipparchus and the early Alexandrian observers, Agrippa's catalogue went a step further by providing precise coordinate measurements for each entry. He didn't just note that a star was in the constellation Virgo, he recorded its celestial longitude and latitude within the zodiacal system, likely using the 360-degree framework that Hypsicles had helped to standardize. This shift from general description to specific numerical data was a monumental leap. It transformed star catalogues from being descriptive guides into being quantitative tools, essential for any serious astronomical calculation, from predicting planetary paths to tracking the very precession of the equinoxes that Hipparchus had discovered. The true value of his meticulous work was its legacy. When the great synthesizer Claudius Ptolemy compiled his epic star catalogue for the Almagest over half a century later, the shadow of Agrippa's work loomed large. Ptolemy himself explicitly mentioned Agrippa, noting his observation of a new star, likely a nova, to help demonstrate that the fixed stars were not entirely unchanging. More importantly, scholars have long debated the degree to which Ptolemy's own star positions relied on Agrippa's earlier data. It is highly probable that Ptolemy used Agrippa's catalogue as a key reference point, a set of older observations against which he could compare his own measurements to check for errors or to calculate the slow drift of precession over the intervening decades. In this way, Agrippa's careful notations became a crucial link in the chain of observational history. providing the before measurement in a cosmic before and after comparison that spanned generations. Agrippa of Bithynia represents a vital but often overlooked class of scientific contributor, the meticulous data collector. He may not have proposed a grand new model of the universe like Aristarchus, or devised a complex geometric system like Apollonius, but his painstaking work in mapping the heavens provided the raw material upon which those grand theories could be tested and refined. His story is a powerful reminder that the foundation of all scientific progress is reliable data, gathered patiently over time by individuals dedicated to the simple, profound act of looking up and writing down what they see, ensuring their measurements would become a gift to the future. While the work of Geminus, Hypsicles, and Sosigenes provided a robust framework for understanding the cosmos, a deeper mathematical language was still needed to truly master its spherical geometry. This crucial leap was made by a first-century thinker whose name is now synonymous with a fundamental theorem of the celestial sphere. Menelaus of Alexandria was a mathematician and astronomer who took the foundational ideas of spherical geometry, which thinkers like Theodosius had established, and transformed them into a powerful, predictive mathematical toolkit. His magnum opus, the three-volume work Spherica, did nothing less than establish spherical trigonometry as a formal mathematical discipline. Before Menelaus, astronomers could describe the shapes on a sphere, but he gave them the equations to calculate within it. The heart of his revolutionary work is the theorem that still bears his name, Menelaus's theorem. While the original version applied to planar triangles, his true genius was in adapting and proving it for spherical triangles. Imagine a triangle drawn on the surface of a sphere, its sides formed by arcs of great circles. Menelaus's theorem provides a precise proportional relationship between the lengths of these arcs when another great circle, a transversal, cuts across them. In essence, it gives you a mathematical recipe. If you know certain parts of this complex spherical configuration, the theorem allows you to solve for all the unknown lengths and angles. This was the master key that unlocked virtually every problem in spherical astronomy. Suddenly, an astronomer could calculate the distance between two stars, the altitude of the sun at any given time, or the precise moment of a star's rising, all through a series of elegant trigonometric calculations derived from his theorem. Menelaus was far more than a brilliant theorist working in isolation. He was also a dedicated observer of the sky. We know from the great Ptolemy that Menelaus made meticulous observations of star positions from Rome in the year 98 of the Common Era. Ptolemy specifically cites Menelaus's measurement of the simultaneous occultation of the star Beta Scorpii by the Moon and the passage of the planet Mars past another star. These were not casual stargazing notes. They were high-precision events, carefully timed and recorded to provide critical data points for refining planetary and lunar models. This combination of hands-on observation and theoretical genius made Menelaus uniquely equipped to bridge the gap between what was seen in the sky and how it could be represented and predicted through mathematics. His work provided the essential calculational backbone for the grand cosmological models that Ptolemy would soon construct. The influence of Spherica cannot be overstated. It became the indispensable textbook for all advanced astronomy in the classical world and beyond. Its rigorous proofs and powerful theorems were the necessary prerequisite for anyone attempting to understand Ptolemy's Almagest, as that monumental work rests entirely on the foundation of spherical trigonometry that Menelaus had built. But his impact soared far beyond the realm of academic astronomy. His work became the silent mathematical engine behind the most important navigational instrument of the next 1500 years, the astrolabe. This intricate device, a portable model of the celestial sphere, relied entirely on the principles of stereographic projection and spherical trigonometry that Menelaus had systematized. Every time a medieval Arab navigator or a Renaissance sea captain used an astrolabe to find their latitude by measuring the altitude of the sun or the pole star, they were performing a practical application of Menelaus's theorems. His legacy was secured through the scholars of the Islamic Golden Age, who recognized the immense power of his work. The Spherica was translated into Arabic in the 9th century, where it was studied, commented upon, and refined by brilliant minds like Ibn Iraq and Nasir al-Din al-Tusi. These Islamic mathematicians built directly upon his foundation, developing the field even further and ensuring its passage back to Europe in the later Middle Ages. In this way, Menelaus of Alexandria provided the fundamental mathematical language that allowed humanity to navigate not only the theoretical cosmos, but also the vast, trackless oceans of our own world, his abstract calculations charting a course for centuries of exploration and discovery. While Menelaus was providing the complex mathematical machinery for celestial calculation, another 2nd century thinker was focused on making the grand ideas of astronomy accessible and meaningful. Theon of Smyrna, a philosopher and mathematician, embarked on a mission not to discover new planets or propose radical models, but to synthesize and explain the entire cosmos for an educated audience. His great work, Mathematics Useful for Understanding Plato, reveals his core belief: to truly grasp the universe as described by the great philosopher, one first needed to understand the mathematical language in which it was written. Theon saw numbers and geometry not as dry abstractions, but as the essential key to unlocking the deepest truths about reality, serving as a crucial bridge between lofty philosophical speculation and the rigorous calculational science of astronomy. His book is a comprehensive guide to the mathematical arts of his time, covering everything from number theory and plane geometry to the far more complex music of the spheres. Theon's genius lay in his ability to compile and clearly explain the vast astronomical knowledge that had accumulated since the time of Plato, acting as an invaluable preservationist for ideas that might otherwise have been lost. He meticulously detailed the planetary models of his predecessors, from the concentric spheres of Eudoxus and Callippus to the elegant epicycles of Apollonius. For a student of philosophy, this provided a clear mathematical foundation for Plato's poetic descriptions of a universe spun from geometric perfection. Theon was answering a fundamental need. Before one could contemplate the why of the cosmos, one needed a clear understanding of the how. Perhaps most fascinatingly, Theon delved into the ancient concept of the harmony of the spheres, the idea that the planets in their motions produce a celestial music inaudible to human ears. But he didn't treat this as mere myth. He approached it with mathematical rigor, exploring the harmonic ratios that could be derived from the planets' perceived speeds and distances. He looked for numerical relationships in their orbital periods, seeking the same simple ratios like 2, 1 or 3, 2 that create pleasing consonances in musical scales. This wasn't just fanciful number play, it was a serious attempt to find an underlying, unifying mathematical order to the seemingly chaotic dance of the planets. For Theon, if the universe was indeed crafted by a divine geometer, as Plato suggested, then that craftsmanship should be evident in the perfect, harmonious proportions governing celestial motion. Theon's work offers us a priceless window into the state of astronomical knowledge just before the monumental synthesis of Ptolemy. He provides detailed descriptions of earlier planetary theories that we would otherwise know only through fragments. His explanations of how epicycles could generate retrograde motion are particularly clear and insightful, serving as an excellent primer for anyone struggling to visualize these complex geometric concepts. He stands as a testament to the vital role of the teacher and the synthesizer in the history of science. For every revolutionary figure like Aristarchus who dares to propose a radical new model, there must be someone like Theon of Smyrna to organize, explain, and pass that knowledge on to the next generation, ensuring that the lamp of learning continues to burn brightly. Now, let's turn our attention to a first-century voice that offers us a rare and invaluable glimpse into how astronomy was taught and understood by a broader, educated audience. Cleomenes, while perhaps not a revolutionary discoverer himself, serves as a crucial conduit, preserving and explaining the celestial knowledge of his era in a way that has survived where so many others have been lost. His work on the circular motions of the celestial bodies is less a book of new theories and more a masterful textbook, a clear and passionate distillation of Greek astronomical wisdom for his students, written from the distinct philosophical perspective of Stoicism. Through Cleomenes, we don't just learn the facts of ancient astronomy, we understand how they were framed and justified for intelligent laypeople. Cleomenes was a staunch and eloquent defender of one of the most important ideas in science, that the Earth is a sphere. He didn't just state this as a fact, he compiled a powerful list of observable evidence to prove it, arguments that remain compelling even today. He pointed to the simple fact that as a ship sails away from shore, the hull disappears below the horizon first, while the masts remain visible for longer, a phenomenon that only makes sense if the surface of the sea is curved. He noted how travelers moving north or south observed new constellations appearing in the sky while familiar ones sink from view, which would be impossible on a flat plane. Furthermore, he argued that during a lunar eclipse, the shadow of the Earth that gradually creeps across the face of the Moon is always invariably curved. The only object that consistently casts a round shadow from any angle is a sphere. For Cleomenes, this wasn't just geometry, it was a testament to the perfect, rational order of a cosmos designed by divine reason. Building on this spherical Earth model, Cleomenes revisited and popularized one of the most breathtaking calculations from a century prior, Eratosthenes' measurement of the Earth's circumference. Cleomenes' detailed account of the method is our primary source for understanding this legendary feat. He explains how Eratosthenes learned that at noon on the summer solstice in the city of Sene, the sun shone directly down a deep well, illuminating the bottom, meaning the sun was at the zenith. On that same day and time in Alexandria, a vertical stick cast a definite shadow. By meticulously measuring the angle of that shadow, Eratosthenes determined it was 1/50th of a full circle. Knowing the approximate distance between the two cities, he simply multiplied that distance by 50 to arrive at a shockingly accurate figure for the planet's girth. Cleomenes' clear explanation of this elegant experiment ensured that this monumental achievement in deductive reasoning would not be forgotten, celebrating the power of human intellect to comprehend the vast scale of its own home. His talent for clear explanation extended to the most fundamental celestial cycles. With remarkable clarity, Cleomenes detailed the mechanics behind the Moon's ever-changing phases. He described how the Moon, itself a dark body, shines only by reflecting the light of the Sun. As it orbits the Earth, the portion of its sunlit hemisphere that is visible from our planet changes, creating the cycle from slender crescent to full moon and back again. He then used this exact same principle to demystify eclipses, those awe-inspiring events that often sparked fear and superstition. A lunar eclipse, he explained, occurs when the full moon passes directly into the cone of the Earth's shadow, temporarily dimming its reflected light. A solar eclipse is the far more precise and dramatic alignment where the new moon passes directly between the Earth and the Sun, casting its small, dark shadow on a portion of our planet and blocking the Sun's light entirely. For Cleomenes, these were not omens but predictable events, the flawless results of celestial bodies moving in their ordained circular paths. What makes Cleomenes' work truly unique is the philosophical lens through which he viewed all of this astronomical knowledge. He was a committed Stoic, and his book is steeped in that philosophy's core tenets. For the Stoics, the universe was a single, living, rational entity, a cosmos of perfect order governed by a divine and immanent logic. Astronomy, therefore, was not merely a technical pursuit. It was a form of piety, a way to understand the magnificent rationality of the divine mind. The predictable motions of the spheres, the perfect geometry of eclipses, the spherical symmetry of the Earth, all of it served as evidence for a coherent, purposeful, and intelligent universe. This Stoic perspective is what motivated Cleombes to write with such persuasive clarity. He wasn't just teaching facts, he was guiding his students toward a state of awe and understanding, helping them align their own reason with the supreme logos that govern the heavens. In preserving both the science of his predecessors and the Stoic worldview that gave it meaning, Cleombes gifted posterity with a complete picture of ancient thought, where the study of the stars was inseparable from the pursuit of a virtuous and enlightened life. From the clear, pedagogical explanations of Cleombes, we now encounter a mind of such staggering breadth that he became known as the athlete, a title earned for his strength not of body but of intellect. Posidonius of Rhodes, a 1st century before the Common Era philosopher, historian, and scientist, was the quintessential polymath, a man who believed that to understand the universe, one must study every facet of it, from the distant stars to the depths of the ocean. A proud Stoic like Cleombes, he nevertheless took the philosophy's reverence for nature in a new, empirically grounded direction, establishing a research school on the island of Rhodes that became a must-visit destination for the Roman elite, including figures like Cicero and Pompey. His approach was encyclopedic. He didn't just contemplate the cosmos, he measured it, seeking the mathematical and physical connections that bound all phenomena together. Posidonius's most celebrated achievement was his own ambitious calculation of the Earth's circumference, a brilliant if flawed attempt to improve upon the method of Eratosthenes. While Eratosthenes used the sun's altitude in 2 different cities, Posidonius turned his gaze to the stars. His ingenious method relied on the star Canopus, the 2nd brightest in the night sky. From his observatory in Rhodes, he noted that Canopus just barely grazed the horizon, never rising more than a fraction of a degree above it. He then learned from sailors that in the Egyptian port of Alexandria, the same star climbed to a height of 7.5 degrees above the horizon at its highest point. Posidonius understood that this difference in altitude, this 7.5-degree angle, represented a specific fraction of the Earth's total 360-degree circle, exactly 1/48th. The final step was the distance between Rhodes and Alexandria, which he estimated from merchant sailing reports. Multiplying that distance by 48, he arrived at a circumference of about 24,000 miles, a figure remarkably close to the actual value of just under 25,000. While his method was sound in theory, his measurements were slightly off. The actual angular difference is closer to 5 degrees, and his distance estimate was likely too large. Yet the sheer elegance of his stellar approach and the accuracy he achieved through simple observation cemented his reputation as a master of cosmic measurement for centuries. His curiosity, however, did not stop at the shoreline. Posidonius was the first thinker to correctly identify the primary force behind the ocean's tides, forging a celestial connection that was centuries ahead of its time. During his extensive travels across the Mediterranean, he meticulously recorded tidal patterns, noting their varying strengths in different locations, like the mighty tides of the Atlantic coast compared to the gentle slosh of the enclosed Mediterranean. He observed that these rhythms were not random but were locked in a perfect, predictable dance with the moon. The highest tides, the spring tides, always occurred during the full moon and the new moon, when the sun and moon aligned to pull the oceans together. The weaker neap tides happened during the quarter moons, when their gravitational pulls act at right angles, partially cancelling each other out. Posidonius proposed that a kind of sympathy or connection existed between the moon's phases and the water of the Earth, a profound intuition of gravitational influence that wouldn't be fully explained for another 1800 years. He even attempted to measure the tidal forces, constructing a simple canal to observe the water's flow and meticulously timing the intervals between high tides, further quantifying this mysterious lunar relationship. His scientific gaze extended into the atmosphere itself, where he applied his systematic mind to the chaotic realm of weather. Posidonius developed a comprehensive theory of meteorology, seeking rational, physical explanations for phenomena that were often attributed to the whims of gods. He studied clouds, rain, wind patterns, and even earthquakes, which he correctly theorized were caused by shifts in the earth, not by the anger of Poseidon. He proposed that vast subterranean caverns could collapse, sending shockwaves through the ground, and he even linked volcanic activity to the violent combustion of underground substances. In every aspect of the natural world, he looked for underlying patterns and causal chains, rejecting superstition in favor of observable, logical cause and effect. This empirical approach to the environment made him a pioneer in the field, attempting to bring the same predictive order to weather that he brought to the stars and the seas. The ultimate legacy of Posidonius lies in the immense influence he wielded over both Greek and Roman thought. Through his writings, which survive only in fragments quoted by others, and through the powerful impressions he made on visiting Roman intellectuals, he became a primary conduit through which Greek science and Stoic philosophy flowed into the Roman world. His encyclopedic works on geography, history, and ethics were devoured by the Roman elite, shaping their understanding of the world they were coming to dominate. He presented a vision of a unified, rational cosmos, governed by discernible laws and connected by invisible threads of sympathy, a vision that deeply appealed to the Roman sense of order and destiny. In Posidonius of Rhodes, we see the ancient world's most complete embodiment of the pursuit of universal knowledge, a man who measured the earth with a star, tied the ocean to the moon, and taught a rising empire that to understand nature was to participate in its divine, rational order. While Posidonius was contemplating the vast sympathies between the moon and the tides, and Cleomenes was crafting elegant explanations of the spherical earth, another kind of genius was at work in Athens, one focused not on grand theories but on practical, public utility. In the 1st century before the Common Era, an astronomer and engineer named Andronicus of Samos was commissioned to solve a very earthly problem for the city's bustling agora. How could its merchants, magistrates, and citizens know the time, regardless of the weather? His brilliant solution still stands today, a marvel of ancient multidisciplinary engineering known as the Horologion of Andronicus, or more poetically, the Tower of the Winds. This structure was far more than a simple clock. It was a civic monument to the human desire to measure and master time itself, a physical embodiment of astronomy's role in the daily rhythm of urban life. The tower itself is a beautiful piece of architecture, an elegant octagonal marble tower that rises in the shadow of the Acropolis. Its 8 sides are not an arbitrary aesthetic choice. Each one is precisely oriented to face one of the 8 principal winds recognized by Greek meteorology. Andronicus didn't just build a tower about the winds, he made it a living instrument for reading them. At the very top, he mounted a magnificent bronze weather vane in the form of Triton, a merman from Greek mythology who held a rod in his outstretched hand. As the wind shifted, this sculptural masterpiece would pivot, with Triton's rod pointing directly to the frieze on the side of the tower that depicted the wind currently blowing. Each of these 8 reliefs is a character in itself, a carved personification of the wind it represents. Boreas, the cold north wind, is shown as a bearded, shivering man wearing a heavy cloak and blowing a conch shell. Notice the stormy south wind is depicted emptying a pitcher of rain, while Zephyrus, the gentle west wind, is a youthful figure scattering flowers from the folds of his gown. This wasn't just functional, it was public art, a way for every citizen to understand and discuss the weather in a shared, visual language. But the true genius of Andronicus lay in the timekeeping technology he integrated. On each of the 8 sun-facing sides of the tower, he carved a meticulously designed sundial. This was a masterstroke of precision engineering. A sundial must be calibrated for the exact latitude where it is built. The angle of its gnomon, the part that casts the shadow, is critical. Andronicus had to calculate the correct angle for each dial to ensure accurate time readings throughout the year. These weren't simple noon markers, they were sophisticated instruments that could divide the day into hours, allowing Athenians to coordinate business, legal proceedings, and social gatherings with a new level of shared punctuality. The sundials turned the entire tower into a giant public clock face, its shadows silently marking the passage of the hours for all to see. Yet Andronicus was a practical man who understood the limitation of his primary technology. The sun doesn't always shine. For cloudy days and the long night hours, he engineered a complete backup system housed within the tower, a complex water clock or clepsydra. Water, flowing from a nearby spring, was carefully regulated to drip into a large reservoir at a constant rate. As the water level rose, it would lift a float connected to an indicator, which in turn moved along a scale to show the time. The engineering challenges were immense, maintaining a perfectly steady water pressure, preventing evaporation or mineral buildup, and ensuring the mechanism was reliable day after day. This hydraulic marvel meant that for the first time, the city had a reliable timepiece that operated independently of the weather, marking the hours through the night and during gloomy winter days. The Tower of the Winds was in effect the world's first known clock tower, a 24/7 timekeeping facility. The legacy of Andronicus of Samos is the legacy of applied astronomy. He took abstract celestial knowledge, the path of the sun, the division of the day, the shifting of the winds, and embedded it directly into the heart of civic life. His tower was a university of time for the common person, a place where the theoretical movements of the heavens were translated into practical, usable information. It stands as a powerful symbol of the Hellenistic era's spirit of innovation, where science was not confined to the library but was deployed in the service of society, making the complex rhythms of the cosmos tangible, visible, and essential to the everyday existence of an entire city. Yet even with the practical genius of Andronicus building his Tower of the Winds, the theoretical understanding of the cosmos was about to be revolutionized by a single, obsessive observer whose name would echo through the ages. We arrive now at a figure who is perhaps the most famous on our list, the man often called the greatest astronomical genius of the ancient world, Hipparchus of Nicaea. While his discovery of the precession of the equinoxes is rightly celebrated, his true legacy is a mountain of meticulous, foundational work that effectively created the discipline of mathematical astronomy as we know it. To focus only on precession is to see the tip of an enormous iceberg. His lesser-known innovations are what gave that discovery its power and formed the bedrock for every astronomer who followed, from Ptolemy to the Renaissance. Hipparchus's monumental achievement was the creation of the first comprehensive and scientific star catalogue of the Western world, a work of such staggering ambition and precision that it would remain unmatched for centuries. But this was no simple list of constellations. His catalogue contained around 850 stars, and for each one, he didn't just note its position. He recorded its precise celestial coordinates, its longitude and latitude within the zodiac, and something no one had ever done systematically before, he estimated its brightness. He devised a simple but powerful 6-grade scale of stellar magnitude, where the brightest stars were of the first magnitude and the faintest visible to the naked eye were of the 6th. This system of quantifying the apparent brightness of celestial objects is the direct ancestor of the logarithmic magnitude scale used by professional astronomers today. It was a revolutionary act of data collection, transforming the sky from a tapestry of myths into a quantifiable database. He didn't just map where the stars were, he began to measure what they were, setting a standard for empirical observation that would not be surpassed until the invention of the telescope. This unprecedented level of precision demanded a new kind of mathematics. The geometry of Euclid and Autolycus was excellent for proofs and models, but it was too cumbersome for the endless calculations required to predict planetary positions or convert observational data into usable coordinates. Hipparchus's solution was to invent trigonometry. Faced with the challenge of solving triangles not on a flat plane but on the curved surface of the celestial sphere, he compiled the first known table of chords. Think of a chord as the ancient equivalent of the sine function. It's the length of the string that subtends a given angle in a circle. His chord table was in effect the first trigonometric table, a calculator's cheat sheet for the ancient world. For every angle from 0 to 180 degrees in increments of half a degree, his table gave the corresponding chord length. With this tool, any complex astronomical calculation involving angles and arcs, determining the distance to the moon, predicting an eclipse, calculating the length of a day could be reduced to a straightforward mechanical process. He provided the mathematical engine that would power all of quantitative astronomy for the next millennium. One of the most brilliant applications of his new trigonometric tools was his groundbreaking work on lunar parallax, a dazzling demonstration of geometric reasoning. Hipparchus realized that if you observe the moon from two different points on Earth, its position against the backdrop of the fixed stars will appear to shift slightly. This tiny angular shift, known as parallax, holds the key to determining the moon's actual distance. During a solar eclipse, he knew that the phenomenon of totality, where the sun is completely blotted out, is only visible from a very narrow path on the Earth's surface. Just outside that path, observers would see a partial eclipse. By carefully gathering reports from different locations about the magnitude of a particular eclipse, he was able to calculate the angular width of the moon's shadow cone, and from that, use his chord tables to triangulate the moon's distance from Earth. His calculation arrived at a figure that was, for its time, remarkably accurate, and his method remains a classic of scientific deduction. He used a celestial event visible to millions to perform a measurement that no single observer could make alone. The tragedy of Hipparchus's legacy is that so much of his pioneering work was later attributed to others. The vast majority of his original writings are lost, and we know of his achievements primarily through the writings of Claudius Ptolemy, who wrote 3 centuries later. Ptolemy's own monumental work, the Almagest, is so comprehensive that it largely overshadowed its primary source. Ptolemy used Hipparchus's star catalogue as the baseline for his own, comparing its coordinates to his contemporary observations to confirm the rate of precession. He adopted and expanded upon Hipparchus's trigonometric methods. In many ways, the Almagest is the brilliant completion and systematization of a research program that Hipparchus had initiated. Consequently, for centuries, many of Hipparchus's key innovations were credited to Ptolemy himself. It is a recurring pattern in the history of science. The great synthesizer who builds the final, magnificent edifice often receives the acclaim, while the original architect who devised the blueprint and laid the foundation is gradually forgotten. Hipparchus of Nicaea was that architect, a relentless, data-driven genius who gave astronomy its first precise map, its first calculating engine, and its first true standard of empirical proof, setting the course for science for generations to come. While Hipparchus was building his immense catalogue of the fixed stars from Greece, a voice from the heart of the ancient Babylonian scholarly tradition was championing a vision of the cosmos so radical that it had been dismissed for over a century. In the bustling Mesopotamian city of Seleucia on the Tigris during the 2nd century before the Common Era, an astronomer named Seleucus emerged as one of the most profound and original scientific thinkers of his age. He stands as a monumental figure for one primary reason. He was the only known astronomer in the entire ancient world, after Aristarchus himself, to publicly advocate for and build upon the heliocentric model, the revolutionary idea that the Earth and planets revolve around the Sun. In an intellectual landscape dominated by the geocentric certainty of Aristotle and the complex epicycles of Apollonius, Seleucus of Seleucia was a brilliant, solitary torchbearer for a forgotten truth. His advocacy for the sun-centered universe was not a matter of blind faith. It was a conclusion drawn from rigorous observation and brilliant theoretical reasoning. Seleucus was a master of the long tradition of Babylonian astronomical data, with its centuries of precise records on planetary positions and cycles. He likely argued that the heliocentric model provided a more natural and elegant explanation for the most perplexing feature of planetary motion, retrograde loops. In the geocentric view, these backward motions required elaborate geometric contortions like epicycles to explain. But from a moving Earth's perspective, the retrograde motion of a planet like Mars is a simple illusion of perspective. Much like one car passing another on a highway makes the slower car appear to move backward. Seleucus likely saw that Aristarchus's model made this confusing phenomenon elegantly simple, a powerful argument for its validity. He may have also pointed to the problem of variable planetary brightness. Planets like Mars grow significantly brighter and dimmer over time, which strongly suggests their distance from Earth is changing, a fact perfectly explained by elliptical orbits around the Sun, but a serious challenge for the fixed, nested spheres of the Aristotelian model. But Seleucus's most stunning and prescient contribution was his theory connecting the Moon to the ocean's tides. He was the first thinker in history to propose a truly physical, mechanistic link between a celestial body and a terrestrial phenomenon. Through meticulous observation, he noted the undeniable correlation. The tides followed a regular pattern that was perfectly synchronized with the phases and position of the Moon. The highest high tides, the spring tides, occurred at the new and full moon, while the lowest high tides, the neap tides, happened at the quarter moons. Seleucus took this correlation a breathtaking step further. He didn't just note the pattern, he proposed a physical cause. He theorized that the Moon's gravitational influence, or as he might have phrased it, the Moon's force or power, actually pulled on the waters of the ocean, causing them to bulge and create the tides. This was a staggering leap of scientific intuition, a correct guess about an invisible force acting across the vast emptiness of space, a concept that wouldn't be fully explained until Newton's law of universal gravitation 2,000 years later. He even reportedly suggested that the strength of this tidal pull was affected by the Moon's changing distance from Earth in its elliptical orbit, another remarkably sophisticated insight. His work represents a fascinating and powerful synthesis of the two great astronomical traditions of the ancient world. He was a Babylonian by training, heir to the world's most extensive and precise archive of observational data. Yet he was intellectually Greek, engaging deeply with the theoretical and cosmological models developed by thinkers like Aristarchus. In Seleucus, we see these two streams converging. The Eastern emphasis on meticulous, long-term data collection merged with the Western drive for grand, unifying cosmological theories. He used the Babylonian data not just for prediction, as his predecessors had, but as evidence to test and support a sweeping physical model of the universe. He was a true scientist in the modern sense, using empirical evidence to argue for a theoretical framework. The ultimate tragedy of Seleucus's story is that his brilliant work, which might have kept the heliocentric idea alive, was almost entirely lost. We know of his theories only through scattered references and critiques in the works of later writers, such as the Greek historian Plutarch and the Roman philosopher Aetius. These authors mention him not to celebrate his genius, but often to dismiss his ideas as curious or outlandish. His voice, arguing for a moving Earth and a lunar force, was drowned out by the overwhelming authority of Aristotle and the practical success of Ptolemy's geocentric system. Seleucus of Seleucia stands as one of history's greatest what-if figures. His work demonstrates that the heliocentric model was not a single, fleeting spark from the mind of Aristarchus, but a viable theory that was actively defended and developed by at least one other major scientific mind. He was a man centuries ahead of his time who looked at the same sky as everyone else but saw a universe governed by physical connections and celestial motions that the world would not be ready to accept for nearly 2 millennia. Long before the elegant epicycles of Apollonius or the precise catalogues of Hipparchus, in the bustling coastal city of Miletus in the 6th century before the Common Era, a mind of unparalleled audacity dared to reimagine the entire cosmos. Anaximander, a student of the legendary Thales, took the first staggering step away from mythological explanations and toward a universe governed by natural, mechanical laws. He looked at the world around him and asked not what the gods intended, but how it all worked, and his answers were so revolutionary they would echo for centuries. He is credited with creating the very first mechanical model of the universe, a vision of cosmic order so profound it effectively invented the field of theoretical cosmology. His most breathtaking leap was his description of the Earth itself. In an age when every other culture imagined our world resting on the back of a turtle, the shoulders of a giant, or floating in a great ocean, Anaximander proposed something utterly radical. He said the Earth was a short, squat cylinder like a stone pillar, and that it hung poised at the very center of the cosmos, completely unsupported. It did not rest on anything. It remained in place, he argued, because it was at the center of all things, and there was no reason for it to move in one direction rather than another. This principle, which we might now call symmetry or equilibrium, was a stroke of genius. He had replaced a physical prop with a geometric and physical principle, envisioning a universe where balance, not divine will, kept the world in place. This was the birth of the concept of a universe that follows consistent, comprehensible rules. But what of the heavens? Anaximander's model was as intricate as it was imaginative. He proposed that the stars, the moon, and the sun were not distant deities but physical phenomena, each contained within a vast, rotating wheel of fire, much like the rim of a chariot wheel. These wheels were wrapped in opaque mist or air, with a single hole or vent through which the inner fire could be seen. A star, then, was not a solitary object but a glimpse of fire through a tiny aperture in its celestial wheel. The sun was a wheel 28 times the size of the Earth, with a hole the size of the Earth itself, which explained its immense brightness. The moon's wheel was smaller, and its phases were simply the periodic opening and closing of its vent. This model explained the daily rising and setting of celestial bodies not as a journey, but as a rotation, a regular, predictable mechanical process. It was the first known system to propose that the celestial bodies were all the same kind of thing, differing only in size and distance, governed by the same mechanical principles. This was not mere armchair philosophy. Anaximander was also a meticulous observer and a practical geographer. He is credited with introducing the gnomon, a simple sundial consisting of a vertical rod, to Greece from Babylon. But he didn't just use it to tell the time of day. By carefully tracking the length and direction of the shadow cast by the gnomon over the course of a year, he achieved a monumental first. He accurately determined the dates of the solstices and equinoxes. He could pinpoint the exact days when the sun reached its highest and lowest points in the sky, and the 2 days of perfect balance in between. This allowed him to map the sun's annual journey with a precision never before achieved, dividing the year into measurable, predictable segments. He even used this knowledge to create one of the first known world maps, depicting the known lands surrounded by a great ocean river, a symbolic representation of his belief in a balanced, orderly cosmos. The true legacy of Anaximander lies not in the accuracy of his specific model, which was of course superseded, but in the revolutionary method he pioneered. He was the first to propose a cosmos that was not alive with capricious gods, but was instead a cosmos, a word meaning both world and order, a system that could be understood through reason, observation, and the application of consistent physical principles. He replaced supernatural narrative with natural mechanism. His floating, cylindrical Earth paved the way for the spherical Earth of the Pythagoreans. His celestial wheels of fire were the direct ancestors of the crystalline spheres of Eudoxus and Aristotle. He set a precedent for using geometry and symmetry to explain the universe's structure, an approach that would define Western science. In the audacious speculations of Anaximander of Miletus, we witness the very moment the first light of scientific inquiry switches on, illuminating a path from myth to mechanism that we are still walking today. While the Greeks were developing their geometric models of crystalline spheres, the ancient Babylonians had been pursuing a vastly different but equally profound astronomical tradition for over 1,000 years, one based on relentless, meticulous observation and the relentless pursuit of cyclical patterns in the heavens. And in the 3rd century before the Common Era, a brilliant priest astronomer named Berosus became the vital human bridge between these two great intellectual worlds. A native of Babylon, Berosus was a high-ranking priest of the god Marduk, a position that granted him unparalleled access to the city's legendary astronomical diaries. These were not casual stargazing notes. They were a vast, centuries-long archive of celestial events, weather patterns, and commodity prices, all meticulously recorded on clay tablets by generations of temple scribes. This was the most extensive scientific dataset the world had ever known. Berosus recognized the immense value of this knowledge, and in a remarkable act of cultural transmission, he made the decision to transport this wisdom westward. He left his homeland and journeyed to the Greek island of Kos, where he established a formal school dedicated to teaching Babylonian astronomy and astrology. This was a monumental moment in the history of ideas. For the first time, Greek thinkers who were masters of geometry and philosophical theory were given direct access to the raw, empirical power of Mesopotamian data. Berosus didn't just bring stories, he brought methods, tables, and cycles that could predict celestial events with an accuracy that must have seemed like magic to his new students. One of his most significant contributions was his work on lunar theory, a field where Babylonian astronomy truly excelled. He is credited with refining the highly accurate Saros cycle, a period of approximately 18 years and 11 days after which the Sun, Earth, and Moon returned to nearly the same relative geometry, causing eclipses to repeat in a predictable pattern. By teaching this cycle to the Greeks, Berosus gave them the power to forecast eclipses not through complex geometric models, but through the simple, powerful recognition of a temporal pattern. This empirical approach, based on centuries of recorded data, stood in stark contrast to the Greeks' more theoretical attempts to model the moon's motion using spheres and circles. Beyond the moon, Berosus was fascinated by the grand cycles governing the entire cosmos. He proposed a vast, almost mystical theory of planetary cycles, suggesting that the history of the universe itself was cyclical. He taught that all the planets would eventually return to the same precise configuration they held at the moment of the world's creation, an event that would trigger a great conflagration or flood, wiping the slate clean for a new cycle to begin. This idea of the Great Year, or World Year, was a blend of Babylonian cyclical cosmology and Greek philosophical thought, and it captivated his audience, influencing later Stoic and Neoplatonic ideas about cosmic renewal. His most tangible and enduring legacy, however, was his role in introducing the zodiacal system to the Greeks. While the concept of the zodiac originated in Mesopotamia, Berosus was instrumental in adapting its 12 signs and their associated astrological lore for a Hellenistic audience. He translated the Babylonian names and meanings into the Greek cultural context, helping to create the system of horoscopic astrology that would explode in popularity across the Roman Empire and shape Western esoteric thought for 2 millennia. In doing so, he ensured that the celestial map used by every subsequent Western astronomer, from Ptolemy to Copernicus, was one drawn originally by Babylonian hands. Berosus of Babylon represents a pivotal type of historical figure, the translator of cultures. He did not make a fundamental new discovery himself, but his act of synthesis was arguably more important. By bringing the data-driven, cyclical approach of Mesopotamian science into conversation with the geometric and theoretical ambitions of the Greeks, he enriched both traditions. He provided the Greeks with the observational bedrock their models needed to become truly predictive, and he gave the Babylonian data a new philosophical framework and a far wider audience. His school on Kos became a crucible where East met West, and the resulting alloy of knowledge would become the foundation for all of classical astronomy, proving that the most profound leaps in understanding often come not from isolation but from connection. Yet even as Berossus was translating the vast knowledge of Babylon for a Greek audience, back in the heart of Mesopotamia itself, a different kind of genius was achieving a level of mathematical precision that would not be matched for centuries. In the 4th century before the Common Era, a figure known as Kidinu, whose name translates to the Righteous One or the True One, was leading a team of scholar scribes at the great astronomical center of Babylon. He represents the absolute pinnacle of the Babylonian astronomical tradition, a mind so advanced that his work feels less like ancient history and more like a precursor to the computational astronomy of the modern era. While the Greeks were building beautiful geometric models of the cosmos, Kidinu and his colleagues were crafting something entirely different, a powerful, predictive mathematical machinery that treated the heavens as a vast clockwork of interlocking cycles, and they were determined to calculate its every tick and tock with breathtaking accuracy. Kidinu's most stunning achievement was his calculation of the length of the solar year. Using centuries of meticulous observations recorded in the astronomical diaries, he and his school devised a method of staggering sophistication. They didn't just count days, they compared the sun's position against the fixed stars at the spring equinox over immense periods of time. Their goal was to find the smallest common multiple that would synchronize the solar year with other celestial cycles, a process requiring immense computational patience. The result was a value for the tropical solar year, the time from one spring equinox to the next, of 365 days, 5 hours, 55 minutes, and a handful of seconds. When we compare this to the modern measurement of 365 days, 5 hours, 48 minutes, and 45 seconds, the difference is a mere 6 minutes and 20 seconds. This is an error margin of less than 1/100th of a single percent. A feat of measurement that would not be surpassed for over 1,000 years. This was not a lucky guess. It was the product of a systematic, data-driven approach that had been refined over generations, reaching its ultimate expression under Kidinu's guidance. This incredible precision was made possible by Kidinu's mastery of what we now call period relations. The Babylonian system was built on the concept of identifying the exact number of times a faster cycle fits into a slower one. For the moon, they used a relation so accurate it became their fundamental timekeeping tool. Every 19 solar years equals almost exactly 235 lunar months. This is the famous Metonic cycle, though the Babylonians knew it long before Meton. But Kidinu's school went even further, seeking even grander cycles to minimize tiny fractions of a day that accumulated over time. Their ultimate masterpiece was the System B lunar theory, a complex set of stepped functions and zigzag functions that modeled the moon's varying speed as it traveled around the Earth. These were not physical models, they were purely mathematical algorithms, a series of rules for adding and subtracting a fixed amount of time per day to predict the moon's position and the timing of lunar eclipses with uncanny reliability. It was astronomy as computation, centuries before the invention of the computer. His work on the Saros cycle for eclipses represents the ultimate expression of this computational genius. The Saros, a period of approximately 18 years and 11 days, is the key to predicting eclipses because it marks the return of the Sun, Earth, and Moon to nearly the same geometric configuration. While the cycle was known to earlier astronomers, Kidanu and his school refined it with an additional layer of precision known as the exeligmos. They realized that after one Saros, an eclipse will recur, but the viewing conditions on Earth will shift slightly westward. However, after 3 Saros cycles, a period of 54 years and 33 days, an almost identical eclipse will recur in nearly the same location on Earth. This triple Saros, the exeligmos, was the Babylonians' long-term eclipse predictor, allowing them to forecast these awe-inspiring events decades and even centuries in advance. Their eclipse tablets are not mystical prophecies. They are cool, dispassionate lists of calculated possibilities, each entry a testament to their faith in mathematical order over divine whim. The legacy of Kidanu is one of profound, yet largely unacknowledged influence. His computational methods, his precise parameters for planetary motions, and his systematic approach to data analysis were the hidden engine behind the success of later Greek astronomy. When Hipparchus and later Ptolemy sought to create their own models, they relied heavily on the long-term observational data and the precise cyclical periods that had been perfected by the Babylonian school of Kidanu. His work represents a parallel path in the history of science, one focused not on physical causes or geometric beauty, but on predictive power through mathematical rule-finding. In many ways, Kidanu of Babylon was the first true mathematical astronomer, a data scientist of the ancient world whose methods of analyzing cycles and building algorithms to predict celestial motion directly anticipate the work of a Johannes Kepler or a modern orbital dynamicist. He looked at the clockwork of the heavens and didn't just describe its beauty, he calculated its next move. While the Babylonians were perfecting their computational cycles and the Greeks were refining their geometric spheres on the other side of the world, in the heart of the Han dynasty, a true Renaissance man was weaving together art, science, and engineering to create a new vision of the cosmos. Zhang Heng, living in the 2nd century of the Common Era, was not merely an astronomer. He was a celebrated poet, a brilliant cartographer, a master mechanic, and a high-ranking court official. His mind refused to be confined to a single discipline, and it was this synthesis of talents that allowed him to produce some of the most groundbreaking and tangible scientific instruments the ancient world would ever see. His most famous invention seems to belong to a different field entirely: the world's first seismoscope, a beautiful bronze vessel adorned with dragons and toads that could detect the direction of a distant earthquake. But this device was not a departure from his astronomical work. It was an expression of the same core belief that the hidden workings of the universe could be measured, quantified, and understood through ingenious mechanical design. Zhang Heng's cosmological vision was as expansive as his intellectual pursuits. In a work titled Ling Zion, or Spiritual Constitution of the Universe, he laid out a theory that was startlingly modern. He described the heavens as an infinite void, a concept that challenged the prevailing models of nested spheres. Within this boundless space, he wrote, the celestial bodies floated freely, driven by a mysterious and powerful energy he called Chi. He used a beautiful and practical analogy to explain the nature of the moon's light, comparing the sun to a fire and the moon to water. Just as fire illuminates water, he reasoned, the sun illuminates the moon. The moon's phases were simply the result of the sun's light falling on different parts of the spherical moon as it moved, while a lunar eclipse occurred when the moon passed into the Earth's shadow. This was a clear, mechanical, and entirely correct explanation that demystified these celestial events without recourse to mythology or omens. To support this theoretical work, Zhang Heng embarked on a project of immense observational scale. He is credited with creating a massive star catalogue that detailed 2,500 stars across 124 distinct constellations. This was not just a list, it was a comprehensive map of the Chinese sky, identifying the brilliant ones we call Ming-Xing and the fainter ones known as Y-Xing. To make such precise observations, he needed advanced tools, and so he improved upon the design of the armillary sphere, that complex model of the celestial sphere. His innovation was revolutionary. He added a power source. By using a water clock to drive a system of gears, he created the world's first water-powered armillary sphere. This wasn't just a static model, it was an automated celestial calculator. It rotated in sync with the actual heavens, demonstrating the motions of the sun, moon, and planets, and providing a continuous, real-time prediction of their positions. It was a planetarium and an astronomical computer all in one. His genius for quantification extended to the very fabric of mathematics and geography. Zhang Heng dedicated significant effort to calculating a more precise value for pi, the ratio of a circle's circumference to its diameter. Using a method of inscription and circumscription of circles with polygons, much like Archimedes had done, he arrived at a value of the square root of 10, which is approximately 3.162. While not as precise as some later calculations, it was a notable improvement for his time and was used in his geographical work. He applied this mathematical rigor to his understanding of the Earth itself, estimating its circumference with a method that, while different from Eratosthenes, reflected a similar desire to measure the scale of the world. He saw the cosmos, the Earth, and the heavens as a single, interconnected system that could be comprehended through number, observation, and mechanical ingenuity. Zhang Heng's legacy is a testament to the height of scientific achievement in ancient China. He represents a path of scientific inquiry that was deeply practical, focused on creating instruments that served both the state and the advancement of knowledge. His seismoscope protected the empire by providing early warning of disasters in distant provinces, while his armillary sphere served to perfect the calendar, a crucial tool for agriculture and imperial ritual. He stands as a magnificent counterpoint to the Greek tradition, demonstrating that the drive to understand the cosmos was a global phenomenon, flourishing independently with its own unique methods and magnificent results. In Zhang Heng, we find the perfect embodiment of the ancient astronomer-engineer, a man who looked at the infinite void and responded not with fear, but with a beautifully crafted machine designed to trace its boundless wonders. Yet, even as the automated armillary sphere of Zhang Heng turned in the Chinese court on the other side of the Himalayas, in the fertile plains of the Gupta Empire, another colossal intellect was reaching for the stars with a radical new vision of the cosmos. In the late 5th and early 6th centuries of the Common Era, a young Indian mathematician and astronomer named Aryabhatta produced a work of such explosive genius that it would redefine the scientific landscape of South Asia for centuries to come. His masterpiece, the Aryabhatiya, written when he was just 23 years old, is a breathtakingly concise and dense collection of verses that covers everything from arithmetic and algebra to the most advanced theories of planetary motion. It opens with a stunning declaration of intellectual independence, an introduction where he names himself and boldly states that he is presenting this knowledge for the benefit of the wise, signaling a break from the anonymous tradition of anonymous Vedic hymns and establishing the role of the individual scientific genius. Aryabhatta's most earth-shattering proposition, one that must have seemed utterly heretical to his contemporaries, was his assertion that the apparent daily rotation of the heavens is an illusion. He argued with brilliant clarity that it is actually the Earth that rotates on its own axis, causing the stars, sun, and moon to appear to move across the sky. He used a simple, powerful analogy. Just as a passenger in a boat moving on a river sees the stationary trees on the bank appearing to move backward, so too do we on this rotating Earth see the fixed stars appearing to revolve around us. This was not a vague philosophical speculation. It was a physical, mechanical model designed to explain observable reality more economically. By removing the need for the entire universe to spin at an unimaginable speed every 24 hours, he presented a more rational and elegant system. While he stopped short of a full heliocentric model, he strongly implied that the orbits of the planets were centered on the Sun, not the Earth, and he described the Sun as the central lamp illuminating the orbiting worlds. This revolutionary view of a spinning Earth in a Sun-centered system, developed entirely independently of Greek ideas, shows a scientific intuition of the highest order emerging from the Indian subcontinent. To support this radical cosmology, Aryabhatta needed precise, undeniable data, and he delivered it with mathematical rigor. He calculated the length of the sidereal year, the time it takes for the Earth to complete one orbit relative to the fixed stars, as 365 days, 6 hours, 12 minutes, and 30 seconds. This is astonishingly close to the modern value, off by only a few minutes. He also calculated the Earth's circumference, arriving at a figure of 24,835 miles, which is less than 1% off from the actual polar circumference of 24,860 miles. These were not rough estimates, they were the products of complex trigonometric calculations and meticulous observation. He even provided the value of pi as 3.1416, more accurate than many of his contemporaries in other parts of the world. This commitment to numerical precision was the bedrock of his entire system, proving that his theories were not just imaginative fantasies but were grounded in quantifiable reality. His computational genius is perhaps best exemplified by his groundbreaking work on eclipses. Rejecting the prevailing mythological explanation of eclipses being caused by a demon, Rahu, swallowing the sun or moon, Aryabhatta provided a perfectly mechanical, geometric cause. He correctly explained that a lunar eclipse occurs when the moon passes into the shadow of the Earth, and a solar eclipse occurs when the moon's shadow falls upon the Earth. But he didn't stop at the basic principle. He developed a sophisticated mathematical model to predict them. He calculated the sizes of the Earth's and Moon's shadows and understood the critical role of the lunar nodes, the 2 points where the Moon's orbit intersects the ecliptic plane. He provided the means to calculate not just whether an eclipse would occur, but its precise magnitude, duration, and even the direction in which the shadow would travel across the disk. This allowed for incredibly accurate predictions that transformed eclipse forecasting from an act of superstition into a demonstrable science. The Aryabhatiya is also remarkable for its advanced system of planetary motion. Aryabhatta assigned 2 types of motion to each planet, a slower mean motion and a faster true motion, which he calculated using a complex system of epicycles. This was not a simple copy of Greek ideas. It was an independent, parallel development of a similar concept to account for the planet's variable speeds and retrograde loops. He described the orbits of the planets as ellipses, a concept that wouldn't be fully embraced in the West until Kepler over 1,000 years later. He even correctly deduced that the planets shine not by their own light but by reflected sunlight, and that the moon's surface with its dark and light patches must be rough and mountainous rather than perfectly smooth. Each of these insights reveals a mind relentlessly applying logic and geometry to peel back the layers of celestial illusion and reveal the underlying mechanics. Aryabhatta's legacy is a testament to the power of independent scientific inquiry. Working without any known contact with the Greco-Roman or Chinese traditions, he arrived at conclusions that were both profoundly similar and dazzlingly unique. His work became the foundation for a flourishing school of astronomy in India, influencing generations of later thinkers like Brahmagupta and Bhaskara. His ideas even traveled westward, likely through Arabic translations, and may have indirectly influenced the Islamic golden age of science. He represents a magnificent parallel path in the history of human thought, a brilliant flare of scientific discovery that illuminated the ancient world from the East, proving that the drive to understand our place in the cosmos is a universal human impulse and that genius can flower anywhere under the same stars. As we reach the end of our journey through the lives of these 30 incredible minds, one thing becomes overwhelmingly clear. The history of astronomy is not a straight line of progress led by a few famous names, but a vast, interconnected tapestry woven by countless thinkers, observers, and innovators from every corner of the ancient world. From the computational genius of Kidanu in Babylon, predicting eclipses with algorithm-like precision, to the mechanical brilliance of Zhang Heng in China, crafting automated armilleries that mapped the heavens, from the revolutionary heliocentric intuitions of Aristarchus and Seleucus to the painstaking star catalogues of Timocharis and Agrippa that gave us our first true map of the night sky, each of these individuals contributed a vital thread to the grand design. They were not isolated geniuses working in a vacuum, but part of a slow, collaborative, and global effort to decode the cosmos, building upon the findings of their predecessors and inspiring the generations that followed, their collective work forming the unshakable foundation upon which Copernicus, Kepler, Galileo, and Newton would eventually stand. So why were they forgotten? The reasons are as varied as the astronomers themselves. For some, like Aglaonice, it was the bias of history, which often recast brilliant women as mystics or witches, diminishing their scientific contributions to mere legend. For others, like Hipparchus, it was the overwhelming shadow of a great synthesizer like Ptolemy, whose comprehensive work, while built directly upon their foundations, inadvertently obscured the original architects. Political upheaval, the burning of libraries like Alexandria, and the simple, slow erosion of time have all played their part in erasing these names from our collective memory. Perhaps the greatest reason, however, is our own tendency to simplify history, to create a clean narrative with a handful of heroic figures, when the reality is far richer, more complex, and far more interesting. We remember the giants, but we forget the many shoulders they stood upon. Their legacy, however, is anything but forgotten. It is written in the very language we use to talk about the sky, in the 360-degree circles standardized by Hypsicles, in the constellations named by Conon, and in the leap years calculated by Sosigenes that still structure our calendar today. It lives on in the mathematical principles of trigonometry forged by Hipparchus and the spherical geometry systemized by Menelaus, tools that are as essential to a modern astrophysicist as they were to an ancient stargazer. Every time we understand an eclipse not as an omen but as a predictable alignment of celestial bodies, we are embracing the rational, evidence-based worldview that these forgotten astronomers fought to establish against a backdrop of superstition and myth. They taught us that the universe operates by knowable rules, and they gave us the first instruments to measure those rules, transforming the starry vault from a realm of gods into a domain of science. This story is a powerful reminder that scientific progress has always been a global, human endeavor. It flourished not just in the academies of Greece, but in the temples of Babylon, the courts of China, the observatories of India, and the public squares of Rome. It was advanced by philosophers and engineers, by poets and priests, by men and women who shared a single, driving curiosity about our place in the cosmos. So now we turn it over to you. Which of these forgotten astronomers captured your imagination the most? Was it the audacious Aryabhatta, who envisioned a spinning Earth over 1,000 years before it was accepted? The clever Aglaonice, who used her knowledge to command awe? Or the meticulous Kidanu, whose calculations rival modern precision? Share your thoughts in the comments below. Let's continue the conversation and ensure that these pioneers of the celestial science are forgotten no more.